100 kilometers. That's all that separates you from a place where your blood begins to boil in your veins. Not a metaphor, not hyperbole. An actual line in the sky, closer than the next city over, where the rules of survival stop working and the universe stops pretending to care whether you live or die. We call it the edge of space, but edges imply borders, boundaries you can see and touch. This is not that. This is a threshold into something so vast and so indifferent that the human brain has no evolutionary framework for processing what it actually means. And here is the thing no one tells you when you start looking up. The terror doesn't stop at that line. It compounds. Every scale you cross, every rung you climb on the ladder of cosmic distance, the fear changes shape. It gets quieter, colder, more absolute. At 4 light-years, you hit a silence so complete it would take 70,000 years just to hear back from the nearest star. At 100 billion dead suns, you realize our galaxy is not a nursery. It is a graveyard built on the ashes of everything that came before. At 2 trillion galaxies, you discover that most of the universe is not stars or planets or anything at all. It is void. Empty space so enormous that entire civilizations could live and die, convinced they are utterly alone. And then you learn the worst part. The universe is not standing still. It is accelerating, pulling itself apart, carrying almost everything that exists permanently out of reach, leaving us in an island of light that is shrinking by the hour. In all that indifferent immensity, we appear to be the one part that ever looked back and understood what it was seeing. This is what happens when you go from 100 kilometers to infinity. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. 100 kilometers. That's the distance between sitting in your chair right now and a zone where the air vanishes, the sky turns black in daylight, and every biological process your body depends on begins to shut down in ways that would horrify you if you had time to think about them. You don't. At that altitude, you have about 15 seconds of useful consciousness before the lack of oxygen shuts your brain off like a light switch. 100 kilometers, 62 miles if you prefer. The length of a decent road trip. A distance you could cover in your car in under an hour if the road went straight up, which it doesn't, because roads need ground, and at 100 kilometers there is no ground. There is barely anything at all. Just you, alone, in a place that has no interest in keeping you alive. This threshold has a name. They call it the Karman line, after Theodor von Karman, a Hungarian-American engineer and physicist who spent his career thinking about flight and who, in the late 1950s, did some math that led him to an uncomfortable conclusion. He calculated that at a certain altitude, the atmosphere becomes so thin that an aircraft would have to fly faster than orbital velocity just to generate enough lift to stay aloft. At that point, you're not flying anymore in any traditional sense. You're falling sideways fast enough that you keep missing the ground. You've crossed from the domain of aerodynamics into the domain of orbital mechanics. You've left the world of wings and entered the world of rockets. The line where that happens sits at roughly 83.8 kilometers, according to Karman's original numbers. The international body that keeps track of aeronautical records, the Fédération Aéronautique Internationale, rounded it up to 100 kilometers because round numbers are easier to write on certificates. So that's where we put it. 100 kilometers, the edge of space, officially speaking. Except it's not really an edge. That's the first uncomfortable truth. The atmosphere doesn't end at the Karman line the way a coastline ends at the ocean. It fades. Slowly, maddeningly slowly, thinning out over hundreds of kilometers until there's so little of it left that calling it atmosphere feels generous. NOAA, the National Oceanic and Atmospheric Administration, calls the Karman line an imaginary boundary. National Geographic calls it the same thing, imaginary. The air doesn't know it's supposed to stop there. Molecules of nitrogen and oxygen are still drifting around at 100 kilometers, just not very many of them, and not nearly enough to do anything useful like fill your lungs or scatter sunlight or slow down a spacecraft. NASA and the United States military put their own line lower, at 80 kilometers, 50 miles, because that's where they decided astronauts earn their wings. The FAA, the Federal Aviation Administration, agrees, 80 kilometers. Meanwhile, one survey of experts reported in Astronomy magazine found estimates ranging from 30 kilometers all the way up to 1.6 million kilometers, depending on what definition of space you were using and who you asked. 30 kilometers is still inside the stratosphere. 1.6 million kilometers is 4 times the distance to the moon. Same question, answers spanning 5 orders of magnitude. So when you ask where space begins, the honest answer is nobody fully agrees, and the widely accepted answer is a round number we picked because it sits near a theoretical transition point calculated by a man who died in 1963. It's a line we drew on a map because we needed to draw one somewhere. The universe did not draw it for us. The universe doesn't do lines, it does gradients, and the gradient between shirt-sleeve atmosphere and hard vacuum is steep but not instant. Which makes it worse in a way, because there's no moment where you can point and say, there, that's it, that's the edge. You're just slowly, incrementally running out of air, and by the time you realize how little is left, you're already too high to do anything about it. Here's what happens if you go up there without a pressure suit. Let's say you're in a balloon gondola or a cramped capsule, and the seal fails at 100 kilometers. The air rushes out. It does that fast, in seconds, because the pressure difference between inside and outside is enormous. Your ears don't pop, they rupture. The gas in your lungs expands violently, and if you tried to hold your breath, your lungs would tear. So step 1 is exhale immediately, and don't stop exhaling because your body is now venting air into a near vacuum, and there's no replacing it. Your skin doesn't explode. That's a myth. But it does swell as the water in your tissues begins to vaporize, not boil in the cooking sense, but shift from liquid to gas, because at that altitude the atmospheric pressure is so low that water can't stay liquid at body temperature. The technical term is ebulism. It's not pretty. Your tongue swells, your eyes swell, fluid starts to bubble under your skin. You're not boiling from heat. You're boiling from the absence of pressure. Meanwhile, the oxygen in your bloodstream is dropping fast. Within about 15 seconds, you lose useful consciousness. Your vision tunnels, your thoughts scatter, and you stop being able to do anything that requires coordination or decision-making, which at that moment would be everything. Within about 90 seconds, you're dead, not from ebulism, that would take longer, but from hypoxia. Your brain runs out of oxygen and shuts down. The whole process from breach to blackout happens faster than you can process what's going wrong, and that's at the edge. That's at the shallowest part of space, the part that's technically still inside Earth's exosphere, where a few stray atoms of atmosphere are still hanging around like distant neighbors. Go higher and it gets worse. Go lower and you're fine. At 90 kilometers you'd last maybe 30 seconds instead of 15. At 80 kilometers, closer to a minute. At 70, you'd stay conscious longer, but you'd still die without pressurization. The gradient is real, but the result is the same. 100 kilometers up, you are in a place that is fundamentally hostile to biological life, and the only reason astronauts survive there is because they bring their atmosphere with them, wrapped in metal shells or worn as suits, portable bubbles of Earth air pressurized to sea level and heated and filtered and monitored by machines that fail more often than anyone likes to talk about. Early attempts to reach this boundary were experiments in controlled terror. In the 1950s, before NASA existed, before anyone had ridden a rocket into orbit, the United States military was trying to figure out what happened to human beings at extreme altitude. They knew pilots were blacking out at high speed and high altitude. They knew pressure suits leaked. They knew almost nothing about what a human body could tolerate at the edge of space, so they built balloons. Enormous balloons, helium-filled envelopes the size of office buildings, designed to carry a single man in a tiny sealed capsule up to altitudes where the sky turned dark and the curvature of the Earth became visible. The program had names like Project Manhigh and Project Excelsior. The men who volunteered were test pilots and Air Force officers, the kind of people who hear the phrase almost certainly survivable and think that sounds good enough. They went up in capsules barely larger than phone booths, dangling under balloons, riding the wind currents up through the stratosphere into the beginnings of the mesosphere, where the air pressure drops to less than 1% of sea level. Some of them made it. Some of them had close calls that would have killed them if a single valve had stuck or a single seal had cracked. Joseph Kittinker, a captain in the US Air Force, jumped from a balloon gondola at an altitude of 31,000 meters in 1960. That's not quite the Karman line. It's only about a third of the way there, but it was high enough that he fell for 4.5 minutes in near vacuum before his parachute opened, and during the ascent, one of his gloves failed. His hand swelled to twice its normal size. He didn't abort. He completed the jump anyway. That level of calm in the face of your own body malfunctioning is either courage or a kind of madness, and at that altitude, the difference stops mattering. The thing that struck many of these early balloonists, the ones who wrote about it later, was not the view. The view was spectacular, yes. The curve of the Earth, the blackness of space overhead, the thin blue line of atmosphere clinging to the planet like a soap bubble. But what struck them was how thin it looked, how fragile. From the ground, the sky seems infinite. You look up and it goes on forever, a dome of blue that stretches to the horizon in every direction. From 100 kilometers up, you see it for what it is, a film, a membrane, a layer of gas, a few dozen kilometers thick, wrapped around a rock, and beyond it, nothing. That realization does something to people. Some astronauts report a profound sense of connection to the planet, an overwhelming awareness of its beauty and fragility. The overview effect, they call it, and it's well documented. But there's another reaction, less talked about, that some of the balloon pilots and early astronauts mentioned in private, a kind of dread. Not the dread of immediate danger, though that was present too, but a deeper existential dread that comes from seeing how little separates the world of life from the void. 100 kilometers, that's all. 100 kilometers of thinning air, and then you're in a place where nothing grows, nothing breathes, nothing survives without technology. The Karman line is not the edge of space in any deep physical sense, but it is the edge of the world, the edge of the place where biology works. Cross it, and you're in a regime where the rules change, where the assumptions your body makes about pressure and temperature and oxygen stop being true. and where your survival depends entirely on whether the machines around you keep working. That's the horror of it. Not that space is far away. It's that it's close, right overhead, 100 kilometers up. You could drive there in an hour if your car had wings and rockets. But here's the part that should bother you more. The thing that makes the Karman line less a boundary and more a warning sign. It's not that the air ends there, it's that the air is thin everywhere. At sea level, the atmosphere presses down on you with a force of about 14.7 pounds per square inch. That pressure is holding you together, keeping your blood liquid, keeping oxygen dissolved in your tissues, keeping your lungs inflated. Climb a mountain and that pressure drops. At the summit of Everest, it's about 1/3 of sea level. Climbers up there are operating at the edge of human tolerance. Their bodies are slowly dying from hypoxia and cold, and they know it, which is why they move fast and don't stay long. Go higher and the pressure keeps dropping. At 10 kilometers, the altitude commercial jets cruise at. The pressure outside is low enough that you'd lose consciousness in under a minute without pressurization. The cabin of a passenger jet is keeping you alive the same way a spacesuit does, by maintaining an artificial bubble of higher pressure, because the air outside at cruising altitude is already in the early stages of not enough. At 30 kilometers, pressure suits. At 50, full spacesuits. At 100, you've crossed into a place where the air pressure is 1/10,000th of sea level, and your body cannot function at all. The Karman line marks the altitude where aviation becomes spaceflight. But the real transition, the biological one, happens much lower. And the thing is, we live at the bottom of this gradient. We live in the thickest part of the atmosphere, the part where pressure and oxygen and temperature all happen to align in the narrow range that allows liquid water and carbon-based life. That zone is not very big. The troposphere, where weather happens and where almost all life exists, extends up to about 12 kilometers at the equator, less at the poles. 12 kilometers, 7.5 miles. If Earth were the size of a basketball, the troposphere would be thinner than the layer of varnish on its surface. We live in the varnish. We call it the world. We build cities in it and grow food in it and fly planes through it, and we do all of that without thinking about how thin it is, because from inside the varnish it seems infinite. It's not. 100 kilometers up, it's functionally gone. 700 kilometers up, it's completely gone. The International Space Station orbits at about 400 kilometers, well above the Karman line, still technically inside the exosphere where individual air molecules are floating around in the dark, but at a density so low that calling it atmosphere is a courtesy. And above that, higher still, the exosphere fades into the solar wind, into the flux of charged particles streaming out from the sun. And at some point, you're not in Earth's atmosphere anymore. You're in interplanetary space, and the transition is so gradual that there's no single moment where you can say it happened. The Karman line is just the first mark on a ruler that extends all the way out to infinity. And once you cross it, every additional kilometer you travel takes you deeper into a place that does not care whether you live or die. That indifference is the part we're not built to handle. Evolution shaped us for a world of air and ground and water. It gave us lungs that pull oxygen from the atmosphere, and skin that regulates heat, and eyes that expect a certain range of light and pressure. None of those systems work in vacuum. Evolution didn't prepare us for vacuum, because vacuum is not a place life goes, it's a place life avoids. The only reason humans have crossed the Karman line at all is because we built machines to take our atmosphere with us, little bubbles of sea-level air, pressurized and heated and filtered, wrapped in metal or fabric, and we ride inside those bubbles, knowing that if they fail, we die. That's the bargain. That's what space travel is. Not exploration in the sense of walking out into a new landscape and breathing new air. Encapsulation. Carrying a piece of Earth with us into a region that is not Earth and hoping the walls hold. The Karman line is where that bargain starts. It's where the air gets too thin to bet your life on, and where every breath after that is a breath you brought with you. And it's only the beginning. 100 kilometers separates you from the edge of space. 400 kilometers gets you to the space station. 384,000 kilometers gets you to the moon, the farthest humans have traveled, the only other world we've ever walked on. Beyond that, the distances stop making sense in human terms. The numbers get so large that kilometers become useless and astronomers switch to light years, the distance light travels in a year, because nothing else scales properly. And at those distances, the isolation becomes so total, the emptiness so vast, that the horror of the Karman line starts to look quaint. Because at least at 100 kilometers, Earth is right there. You can see it, you can fall back to it. You're still inside its gravity well, still orbiting its center, still close enough that if something goes wrong, there's a chance, however slim, of getting home. Go farther, past the moon, past the orbit of Mars, out into the space between worlds, and that safety net disappears. You're not at the edge anymore, you're in the middle, and the middle is where the real terror lives. The moon is close. You've seen it, you know where it is. Point up, somewhere in that general direction, and you're probably within a few degrees. 384,000 kilometers away, give or take a few thousand depending on where it is in its orbit. The astronauts who went there in the late 1960s took 3 days to get there, coasting most of the way after the initial burn, and they came home in 3 more. Round trip, a week. Long enough to get uncomfortable, short enough that you could pack food and not worry about running out. The moon is the farthest place humans have ever traveled, and in the scale of what comes next, it might as well be sitting on your front porch. Because the next thing out, the next real destination, the closest piece of the universe that isn't gravitationally bound to our sun, is so far away that the numbers stop meaning anything useful. 4.2 light-years. That's the distance to Proxima Centauri, the nearest star to Earth after our own. 4.2 light-years. Say it out loud and it sounds manageable. 4 of something. 2/10 more. That's a measurement you could write on a napkin. The number fits in your head, the distance does not. A light-year is how far light travels in 1 year. Light moves at roughly 299,792,458 meters per second in vacuum. Call it 300 million for the sake of not spending the next 5 minutes on a number. At that speed, light crosses the distance from the Sun to Earth, 1 astronomical unit, roughly 150 million kilometers, in about 8 minutes and 20 seconds. You are seeing the Sun as it looked 8 minutes ago right now, always, because that's how long it takes the light to get here. If the Sun exploded, you wouldn't know for 8 minutes. You'd keep seeing it shine, keep feeling its warmth, keep living under a star that no longer existed, because the information that it had died would still be crossing the gap. Light from the moon takes about 1.3 seconds to reach you. Light from Mars, depending on where the planets are in their orbits, takes anywhere from 3 minutes to 22 minutes. Light from Neptune, the farthest planet, takes about 4 hours. All of that, every planet, every moon, every asteroid and comet in our solar system, all of it sits inside a bubble roughly 8 light hours across. That's the neighborhood. That's home territory. That's the region of space where we've sent machines, mapped the surfaces, analyzed the chemistry, and in a few cases landed and looked around. Proxima Centauri is not in that bubble. It is 40,000 times farther away than Neptune. 4.2 years at the speed of light. Not 4.2 years of travel time for a spacecraft. 4.2 years for light itself, the fastest thing in the universe, the thing that crosses 7.5 times around the Earth's equator in 1 second. Take that speed, sustain it without slowing down for 4.2 years, and you arrive at the nearest star. Not the nearest interesting star, not the nearest sun-like star, the nearest star, period. After that, the next closest system is Alpha Centauri A and B, a binary pair that Proxima actually orbits at a great distance, sitting just slightly closer to us than its larger companions. Then Barnard's star at 6 light-years, Wolf 359 at 7.9. Sirius, the brightest star in Earth's night sky, sits 8.6 light-years away. These are the neighbors. This is the local group. And every single one of them is unreachably far by any current definition of the word reachable. The fastest spacecraft humans have ever built is Voyager 1, launched in 1977 and still operational as of this moment, transmitting data back from interstellar space where it crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, back in 2012. Voyager 1 is currently moving at roughly 17 kilometers per second relative to the Sun. That's fast. That's about 61,000 kilometers per hour. At that speed, you'd cross the United States coast to coast in under 3 minutes. You could lap the Earth at the equator in about 12 minutes. Voyager 1 has been flying for more than 47 years, and it has traveled roughly 24 billion kilometers from Earth. It is the most distant human-made object in existence. And if it were headed toward Proxima Centauri, which it is not, it is headed in a completely different direction. It would take roughly 73,000 years to get there. 73,000 years. That is longer than recorded human history. That is longer than agriculture. That is deep into the last ice age, back when woolly mammoths were still walking around and humans were just beginning to figure out that you could plant seeds on purpose. Launch Voyager 1 toward Proxima Centauri today, and it would arrive sometime around the year 75,000. Your great-great-great-grandchildren, thousands of generations removed, would be dead and forgotten, and the spacecraft would still be in the dark, coasting silently between stars. Let's try something faster. The Parker Solar Probe, launched in 2018 to study the Sun, holds the record for the fastest speed ever achieved by a human-made object. During its close passes around the Sun, using gravity assists to whip itself into tighter and faster orbits, Parker has reached speeds of up to 192 kilometers per second, roughly 0.064% the speed of light. That is breathtakingly fast by human standards. At that speed, the probe crosses the distance from New York to Los Angeles in under 20 seconds. If you pointed Parker Solar Probe at Proxima Centauri and somehow kept it at that speed, which you couldn't because it only reaches that velocity during close solar passes and would slow down dramatically once it left the Sun's gravity well, it would still take roughly 6,700 years to arrive. 6,700 years ago, humans were building the first cities in Mesopotamia. Writing had just been invented. The pyramids at Giza wouldn't be built for another 2,000 years. That's the timescale we're dealing with, and that's using the fastest thing we've ever built, pushed to a speed it can only sustain for brief moments under ideal conditions. Now let's get hypothetical. Let's say we built a spacecraft that could sustain 1% the speed of light. 1%. Not the speed of light, just 1/100th of it. That's still roughly 3 million kilometers per hour. That is so far beyond current propulsion technology that we don't have a realistic plan for how to achieve it. The concepts exist. Nuclear pulse propulsion, using a series of atomic bomb detonations behind a massive pusher plate to accelerate a spacecraft. Antimatter drives, if we could ever produce antimatter in meaningful quantities, which we can't. Light sails pushed by enormous ground-based lasers, a concept that works on paper and might be testable at small scales but scales up into engineering problems we have no solutions for. Let's ignore all of that and just assume we solved it. 1% the speed of light. At that velocity, Proxima Centauri is 420 years away. 4 centuries. Launch the mission today and it arrives in the year 2445. That's 12 generations if you're generous with life expectancy. No one alive at launch would be alive at arrival. Their children wouldn't be alive. Their grandchildren wouldn't be alive. You'd need a generation ship, a fully self-sustaining habitat capable of supporting a human population for centuries, recycling air and water and waste, growing food, maintaining the ship's systems, raising children who would live their entire lives knowing their only purpose was to keep the mission going so that their children could do the same. And that's assuming nothing broke. No failed reactor, no hull breach, no pandemic, no mutiny. 420 years of nothing going catastrophically wrong. Human institutions barely last that long on Earth, where you can get replacement parts. Push it to 10% the speed of light and you're down to 42 years. That's within a single human lifetime, barely. Launch at 20, arrive at 62, if you survive. 10% the speed of light is 30,000 kilometers per second. You would lap the Earth more than once per second. At that speed, hitting a grain of sand would release the energy of a hand grenade. Hitting anything larger would vaporize the front of your spacecraft. Interstellar space is not empty. It's close, but not empty. There are atoms out there, hydrogen mostly. Roughly 1 atom per cubic centimeter on average, though it clumps in clouds and thins out in voids. At 10% light speed, those atoms hit your hull with enough energy to do damage. You'd need shielding, heavy shielding, which adds mass, which requires more energy to accelerate. The faster you want to go, the harder the engineering gets, and we haven't even touched on how you slow down when you get there, because coasting into a star system at 10% the speed of light doesn't give you time to look around. You scream past in a matter of hours and you're gone, out the other side, back into the dark. At the speed of light itself, impossible for anything with mass, but let's pretend. Proxima Centauri is 4.2 years away. That's the floor. That's as good as it gets. You cannot go faster. The speed of light is not just a speed limit, it's a structural feature of space-time itself. Go that fast, and time stops for you relative to outside observers. You'd experience the trip as instantaneous, or close to it. But everyone you left behind would age 4.2 years. Send a signal home, and it takes 4.2 years to arrive. Get a reply, and it takes 4.2 years to come back. 8.4 years round trip for a conversation. That's the latency. That's the communication delay for the nearest star. By the time mission control hears that something went wrong, the crew has been dead for 4 years, and there's nothing anyone can do but listen to the recording. Here's what 4.2 light-years actually means in human terms. It means isolation so complete that it breaks the concept of help. If you're at Proxima Centauri and you have an emergency, no one is coming. No rescue mission, no resupply. No advice that arrives in time to matter. You are on your own in a way that no human being in history has ever been on their own. Even the most remote Antarctic research stations can call for an airlift. Even the astronauts on the moon were only 3 days from home. Proxima Centauri is 40 trillion kilometers away. 40 trillion. Written out, that's 40, followed by 12 zeros. 40 million million. The number is so large that your brain doesn't process it as distance anymore. It processes it as a concept, far, unreachably far. And Proxima Centauri is not a nice place. It's a red dwarf, a small dim star with about 12% the mass of our Sun and about 1/10 the luminosity. It's so faint that even though it's the closest star to Earth, you can't see it without a telescope. It sits in the constellation Centaurus, visible only from the southern hemisphere, and it doesn't show up on any star chart you'd use for casual stargazing. Proxima is old, probably around 4.8 billion years old, about the same age as the Sun. It will keep burning for trillions of years because red dwarfs are efficient, fusing hydrogen so slowly that they outlast every other type of star. But while they burn, they're unstable. Proxima flares, frequently, powerful bursts of X-rays and ultraviolet radiation that would sterilize any nearby planet not protected by a thick atmosphere and a strong magnetic field. We know Proxima has at least 2 planets. Proxima Centauri b, discovered in 2016, sits in the star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. It's about 1.3 times the mass of Earth and orbits its star every 11.2 days. 11 days. That's how close you have to be to a red dwarf to be in the habitable zone. That proximity makes the planet tidally locked, one side always facing the star, one side always in darkness, and it means the planet gets blasted by Proxima's flares at close range. Whether it has an atmosphere at all is an open question. Whether it has liquid water is a guess. Whether it has life is something we'll likely never know unless we go there, and we're not going there. The gap between us and Proxima Centauri is not just distance, it's silence. Interstellar space is the quietest place in the universe. Sound requires a medium, air or water, or something for pressure waves to move through. Space is vacuum. Not perfect vacuum, but close enough that the density is measured in atoms per cubic centimeter instead of molecules per breath. There is nothing to carry sound. If a star exploded 1 light-year away, you wouldn't hear it. You'd see the light, eventually. You'd detect the radiation, the particles, but you wouldn't hear a thing. Space is silent the way death is silent, not because there's nothing happening, but because there's no mechanism for you to perceive it as noise. Astronauts on the ISS report that the silence outside is absolute. Inside the station, you hear fans and pumps and the hum of electronics. Open the hatch, step outside, and the universe goes mute. You hear your own breathing. You hear your heartbeat. You hear the crackle of the radio in your helmet. Everything else is silence. That silence extends from low Earth orbit all the way out to the edge of the observable universe. 40 trillion kilometers to Proxima Centauri. Every centimeter of it dead quiet. No sound, no air, no landmarks. Nothing to navigate by except the stars themselves, and at interstellar distances, even the stars start to move. Proxima Centauri has a proper motion, a velocity relative to the Sun, of about 22 kilometers per second. It's moving. Over thousands of years, it drifts across the sky. The star you aim at when you launch is not where the star will be when you arrive. You have to calculate the intercept. Lead the target the way you'd lead a moving clay pigeon with a shotgun, except the clay pigeon is a star 4 light years away, and if you miss, there's no second shot. You're gone. Out into the space between galaxies, or worse, into a trajectory that sends you back toward the Sun at some absurd angle where you can see home but never reach it. Humans have thought about interstellar travel seriously since at least the 1970s. Project Daedalus, a study by the British Interplanetary Society, proposed a two-stage nuclear pulse rocket that could reach 12% the speed of light and arrive at Barnard's star in about 50 years. It was a paper study. Nothing was built. The spacecraft would have massed 54,000 tons, most of it fuel, and it required technology we still don't have. Breakthrough Starshot, announced in 2016, with backing from Yuri Milner and Stephen Hawking, proposed using ground-based lasers to accelerate tiny light sail probes to 20% the speed of light. The probes would be about the size of a postage stamp, weigh a few grams, and carry cameras and sensors enough to snap photos as they screamed past Alpha Centauri 20 years after launch. The engineering challenges are enormous. The lasers would need to be more powerful than anything currently in existence. The sails would need to survive acceleration forces that would rip apart most materials. The probes would need to transmit data back across 4 light-years using a power source that fits in a package the size of a smartphone. It's theoretically possible. It's nowhere close to funded or built. And even if it works, even if the probes get there and send back pictures, we wouldn't see those pictures for 4.2 years. The data arrives at the speed of light. There's no shortcut. Generation ships are the fallback, the concept you turn to when you accept that no one alive at launch will see the destination. You build a habitat. You load it with people, hundreds or thousands, enough genetic diversity to avoid inbreeding over multiple generations. You give them everything they need to live, to grow food, to recycle waste, to repair the ship, to raise children who will do the same. You point it at a star and you let it go. 40 years, 400 years, 4,000 years, it doesn't matter. The ship becomes its own world. The original crew dies, their children die. Generations pass, and eventually the knowledge of Earth fades into myth, a story the elders tell about a place their ancestors came from, a blue world none of them have ever seen. And then one day, centuries later, the ship arrives. The descendants of the original crew, people who have never breathed unrecycled air, never felt gravity that wasn't generated by spinning their habitat, never seen a horizon that wasn't the curved inner wall of a cylinder. They step out into a new star system and try to build a life there. If the planet is habitable, if the ship still works, if the society on board didn't collapse somewhere in year 200 when the third generation decided they didn't want to spend their lives maintaining a machine for people who didn't exist yet. Or you freeze them, suspended animation, lower the body temperature, slow the metabolism to near zero, put them in a medical coma that lasts decades or centuries, wake them up when the ship arrives. It works in fiction. It barely works in reality. We can freeze human embryos. We can freeze sperm and eggs. We've put people in medically induced comas for weeks. We've cooled patients undergoing surgery to slow their metabolism and buy time. But we've never frozen a living human being and successfully revived them. Every cell in your body contains water. Water expands when it freezes. Ice crystals form and rupture cell membranes. Your tissues turn to mush. Cryonics companies will freeze your body after you die and promise to revive you someday when technology improves, but no one has ever demonstrated that revival is possible. The people frozen in liquid nitrogen right now are, by every measure we have, dead. We don't know how to bring them back. We don't even know if bringing them back is physically possible. Freeze a person for 400 years, and the odds are very good that you arrive at Proxima Centauri with a hull full of corpses. The only realistic way to cross interstellar distances with current physics is slowly, multi-generational missions that accept the time scale and plan for it. Or we wait. We wait for technology that doesn't exist yet, propulsion systems that can push closer to light speed, breakthroughs in physics that let us cheat the distance somehow, wormholes, warp drives, concepts that sound like science fiction because right now they are. General relativity doesn't forbid wormholes. It just requires exotic matter with negative energy density to hold them open. And we've never seen exotic matter outside of quantum fluctuations that last for fractions of a second. Warp drives, the Alcubierre metric, same problem. You need negative energy. You need to warp space-time itself. The math says it's possible. The engineering says good luck. And even if we built one, even if we solved the impossible physics and powered the impossible machine, you still have to cross 4.2 light-years. The distance doesn't go away just because you found a clever way to move through it. So we sit here, we look up, we see the stars, and we know, with high confidence, that most of them have planets. We know some of those planets are rocky. We know some of them sit in habitable zones where water could be liquid. We know, statistically, that life probably exists out there somewhere because the universe is too big for Earth to be the only place it happened, and we know we will likely never meet it because the stars are too far apart, because the galaxy is too big, because the speed of light is too slow and our lives are too short, and the space between stars is a gulf so wide that it swallows ambition. Proxima Centauri is right there, the closest one, 4.2 light-years, and we can't reach it, not in our lifetimes, not in our children's lifetimes. Maybe not ever. The abyss between stars is the largest empty space most people will ever try to conceptualize, and it is only the beginning. Because Proxima is one star, the Milky Way contains somewhere between 100 billion and 400 billion stars, depending on who's counting and what counts as a star. And most of them are farther away than Proxima, much farther, thousands of light-years, tens of thousands. The galaxy is 100,000 light-years across, and it is full of stars, billions of them, scattered through the dark like sand on a beach. And almost all of them are unreachable. They sit out there, burning, living, dying, and we will never visit them. We will never know what orbits them. We will never walk on their planets, or breathe their air, or meet whatever lives there. We are stuck here, in this one system, circling this one star, looking out at a galaxy full of places we can see but never touch. That is the isolation. That is the gulf. And past the stars, past the bright points you can see from Earth with the naked eye, there are places darker still, places where the stars themselves have died. And those places, those stellar graveyards scattered throughout the Milky Way, tell a different kind of story. Not about distance, about endings. The stars you see in the night sky are not permanent. That is the first thing you need to understand about the Milky Way. Every point of light up there, every constellation, every distant glow that's been shining long enough to earn a name in human mythology, is temporary. Stars are not eternal fixtures hanging in the dark. They are machines. Vast fusion reactors burning through fuel at rates determined by their mass, and when the fuel runs out, they die. Some fade quietly, some explode with enough violence to outshine entire galaxies for weeks, and when they're gone, what's left behind is not nothing, it's something worse than nothing. A corpse, a stellar remnant, a piece of the universe that has stopped producing light but refuses to stop existing. The Milky Way is full of them. Tens of billions of dead stars scattered through the spiral arms and the halo, invisible to casual observation, pulling on the fabric of space around them, influencing the orbits of living stars, sitting in the dark like monuments to processes that finished billions of years ago. This galaxy is not a collection of bright young suns, it is a graveyard, and we live in the middle of it. Here's how a star dies. The process depends entirely on mass. Small stars, the kind that weigh less than about half the mass of our Sun, burn hydrogen so slowly that they can last for trillions of years. The universe is not old enough yet for any of these stars to have reached the end of their lives. They're still burning, and they will keep burning long after every other type of star has gone dark. When they finally do run out of fuel, somewhere in the unimaginably distant future, they will collapse into white dwarfs, hot, dense cores about the size of Earth, packed with matter so tightly that a teaspoon of it would weigh several tons. White dwarfs don't burn, they just glow, radiating away the leftover heat from their previous lives over billions of years until they fade completely into black dwarfs, cold, dark spheres drifting through space forever. No black dwarf has ever been observed because the universe is not old enough to have produced one yet. But it will, eventually. That's the quiet death. The death reserved for stars that played it safe, burned slow, and outlasted everyone else. Our Sun will die that way. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. The core will contract and heat up. The outer layers will expand, turning the Sun into a red giant large enough to swallow the inner planets. Mercury goes first, Venus second. Earth might survive on the outer edge of the expanding envelope, or it might not. Either way, the surface will be sterilized, the oceans boiled off into space, the atmosphere stripped away. What's left will be a scorched rock orbiting a dying star. The red giant phase lasts a few 100 million years, then the Sun runs out of helium. The core collapses one last time. The outer layers puff off into space as a planetary nebula, a glowing shell of gas expanding outward. And at the center, where the Sun used to be, there's a white dwarf, about the size of Earth, mass just over half what it is now. Hot enough to glow white, then yellow, then red, then eventually nothing. That object will outlast every civilization that ever existed on Earth. It will outlast the continents. It will outlast the solar system as a recognizable structure. And it will still be there, a tiny dense sphere, cold and dark, billions of years after the last human being who ever thought about the Sun has been dead and forgotten. That's the fate of most stars in the galaxy. Somewhere between 70 and 80% of all stars will end as white dwarfs. But the ones that don't, the ones that started with more mass, 8 times the Sun's mass or higher, they go out differently. They go out loud. Massive stars burn through their fuel fast. A star with 10 solar masses might live only 20 million years. A star with 50 solar masses might last 3 million. These stars don't have time to settle into a stable old age. They burn hydrogen, then helium, then carbon, oxygen, neon, magnesium, silicon, building heavier and heavier elements in their cores with each stage, climbing the periodic table one fusion reaction at a time. Each stage runs hotter and faster than the last. Hydrogen fusion lasts millions of years. Helium fusion lasts hundreds of thousands. Carbon fusion lasts a few hundred years. Silicon fusion, the last stage, lasts about 1 day. 1 day of fusing silicon into iron in the core of a massive star, and then it's over. Because iron doesn't fuse, you can't get energy out of fusing iron. It just sits there, piling up in the center, getting heavier, denser, hotter, until the core reaches a critical mass and collapses in less than a second. The collapse is catastrophic. The core, which was the size of Earth, compresses down to about 20 kilometers across. Electrons and protons are crushed together into neutrons. The temperature spikes to hundreds of billions of degrees. The outer layers of the star, suddenly unsupported, fall inward at a significant fraction of the speed of light, hit the incompressible neutron core, and bounce. That bounce is a supernova. The explosion releases more energy in a few seconds than the star radiated during its entire life. For a brief moment, the supernova outshines every other star in its host galaxy combined. If you were watching from another galaxy, you would see one star suddenly flare up and become visible where a moment before there was only the diffuse glow of billions of normal stars. The light from a supernova can be detected from billions of light years away, and at the center of that explosion, crushed down to a sphere the size of a city, is what's left of the core, a neutron star. Neutron stars are the densest objects in the universe that are not black holes. About 10 to 15 kilometers in radius, mass somewhere between 1 and 2 times the Sun. The surface gravity is so strong that if you dropped an object from a height of 1 meter, it would hit the ground at several million kilometers per hour. The escape velocity is about 1/3 the speed of light. The magnetic field is trillions of times stronger than Earth's, strong enough to distort the shape of atoms, and they spin fast. Newborn neutron stars can rotate hundreds of times per second, blasting beams of radiation out of their magnetic poles as they spin. If one of those beams sweeps across Earth, we see it as a pulsar, a rhythmic pulse of radio waves arriving with clockwork precision. The first pulsar ever detected, discovered in 1967 by Jocelyn Bell Burnell, pulsed every 1.3 seconds. For a brief moment, astronomers thought they might be looking at a signal from an alien civilization, because nothing natural was supposed to produce a signal that regular. Then they found more. Dozens, then hundreds, then thousands, all neutron stars, all spinning. All the leftover cores of stars that died in supernovae. Some neutron stars don't stop at neutron star. If the core is massive enough, more than about 3 solar masses, the collapse doesn't stop. The neutrons can't hold it up. There's no force in physics strong enough to resist the gravity. The core collapses past the neutron star stage and keeps going, compressing down past any size, past any density we can calculate, until it punches through space-time itself and becomes a black hole. A region where gravity is so strong that not even light can escape. The boundary of that region, the point of no return, is called the event horizon, and once you cross it, you are gone. Not gone in the sense of far away, gone in the sense of no longer part of the universe that anyone outside can interact with. You've fallen into a place where time and space trade roles, where every direction points toward the center, and where the concept of future becomes indistinguishable from the concept of inward. Black holes don't emit light, they don't radiate heat, not in any practical sense. Hawking radiation exists in theory, but it's so faint that a black hole the mass of the Sun would take longer than the current age of the universe to evaporate. For all measurable purposes, black holes are permanent. They sit in the galaxy, invisible, detectable only by the way they pull on things around them, bending light, dragging stars into orbit, feeding on anything that drifts too close. Here's the number that should make you pause. The Milky Way is about 13 billion years old. It's been making stars for almost as long as the universe has existed. Stars form in bursts, in molecular clouds where gas collapses under its own gravity. And in those bursts, you get a mix. Lots of small stars, fewer medium stars, and a handful of massive ones. The massive ones die first. They burn out in a few million years, explode, and leave behind neutron stars and black holes. The medium stars take longer, hundreds of millions or billions of years, but eventually they die too, puffing off their outer layers and leaving white dwarfs. The small stars are still here, burning slowly, but everything bigger than them, everything that formed in the first 10 billion years of the galaxy's history and had enough mass to die already, has died. Astrophysicists have run the models, they've counted the stars, they've estimated the death rate, and the number they come back with is this. The Milky Way contains somewhere between 100 billion and 400 billion stars, depending on how you count them and what mass cutoff you use. Most of those stars are still alive, but the galaxy has been running for 13 billion years, and during that time it has produced and killed an enormous number of massive stars. Current estimates put the dead star population at somewhere around 100 billion remnants, 100 billion white dwarfs, neutron stars, and black holes scattered throughout the galaxy. For every star you can see in the night sky, there is at least one dead star you cannot see, sitting somewhere in the dark, finished. In 2020, a team of astrophysicists at the University of Sydney published the first comprehensive map of what they called the galactic underworld. They modeled the formation, evolution, and death of stars in the Milky Way over its entire history, tracking where the remnants ended up. What they found was surprising. First, the remnants don't stay where the stars died. When a massive star goes supernova, the explosion is not symmetric, it's lopsided. The blast kicks the neutron star, or black hole, in a random direction at speeds that can reach hundreds of kilometers per second. That's fast enough to escape the gravitational pull of the star's birthplace and drift out into the galaxy. Over billions of years, those remnants spread out. The living stars in the Milky Way are concentrated in the disk, a flat, rotating structure about 1,000 light-years thick. The dead stars, by contrast, are spread through a much larger volume, a puffed-up halo that extends roughly 3 times higher above and below the galactic plane. The second surprise was that about 1/3 of the remnants have been kicked so hard that they're leaving the galaxy entirely. Their velocities are high enough that they will eventually escape the Milky Way's gravity and drift off into intergalactic space, orphaned, no longer part of any galaxy, just wandering through the void forever. The nearest stellar remnant to Earth, according to the models, should be about 65 light-years away. 65 light-years, that's close. That's inside what astronomers consider the solar neighborhood. And yet we don't know where it is. We haven't found it. If it's a white dwarf, it might be faintly visible in surveys. If it's a neutron star or a black hole, it's effectively invisible unless it's doing something dramatic, like pulling matter off a companion star or passing in front of a background object and bending its light. Most remnants are quiet. They sit in the dark. They don't announce themselves. They're only detectable if you go looking with instruments sensitive enough to pick up the faint gravitational tug or the occasional flicker of radiation. The fact that there is likely a stellar corpse within 65 light-years of Earth, and we haven't identified it yet, tells you how hard these objects are to find. The galaxy is full of them, tens of billions of them, and most of them are invisible. That invisibility matters because it changes what the Milky Way is. When you look up at night and see the river of stars cutting across the sky, you're seeing the bright young population, the stars that are still burning, still fusing hydrogen, still producing light. That's the part of the galaxy we notice because it's the part we can see. But the majority of the galaxy's history is not written in those bright stars. It's written in the remnants. The white dwarfs cooling slowly in the halo, the neutron stars spinning silently in the disk, the black holes drifting through interstellar space, pulling on nothing, visible to no one. The Milky Way is not just a galaxy of stars, it's a galaxy of endings, a structure built as much from death as from life. And the dead outnumber the living. or they will soon, once enough time has passed and enough of the remaining stars burn out. What you're seeing when you look at the Milky Way is not the galaxy as it is, it's the galaxy as it was, because the light takes time to reach you. And what you're not seeing, because it doesn't emit light, is the graveyard underneath. There's another piece to this. The deaths are not wasted. When a massive star explodes, it doesn't just leave behind a neutron star or black hole. It also scatters its outer layers into space, and those layers contain every element the star built during its life. Carbon, oxygen, nitrogen, iron, silicon, calcium, gold, silver. All the heavy elements, everything heavier than helium, was made inside stars or during supernova explosions. The supernova blasts that material out into the interstellar medium, where it mixes with clouds of hydrogen and eventually gets pulled back into new star systems. The Sun is a third-generation star, maybe fourth, built from gas that had already been through previous cycles of star formation and death. The Earth and everything on it, every rock, every ocean, every atom in your body, was forged inside stars that died billions of years ago. You are made of recycled stellar ash. The calcium in your bones came from a supernova. The iron in your blood came from the core of a massive star that collapsed and exploded before the solar system existed. The oxygen you're breathing right now was made inside a dying star and blown into space when that star's outer layers puffed off. This is not poetry. This is chemistry. You are literally built from the remnants of dead stars, which makes you, in a very real sense, part of the graveyard. The process repeats. Stars die, their material spreads, new stars form from the enriched gas. Those stars die, the cycle continues. The galaxy has been running this loop for 13 billion years, and the result is that the material you're made of has been through multiple stars. It's been fused, scattered, recollapsed, fused again, scattered again. Your atoms are old, older than the Sun, older than the Earth, older than the solar system. They've been around since close to the beginning of the galaxy, cycling through generation after generation of stars, and they'll keep cycling long after you're gone. The Milky Way is a machine that turns hydrogen into heavy elements and then recycles those elements into new structures, stars, planets, moons, life, if the conditions are right, and eventually death. Everything that forms eventually breaks apart. Everything that lives eventually stops. The galaxy does not care. It keeps running the cycle, building new stars out of the ashes of old ones, indifferent to what those stars produce or how long it lasts. And at the center of all of it, holding the galaxy together, is something that shouldn't exist. The galactic center is about 26,000 light-years from Earth, hidden behind dense clouds of gas and dust that block visible light but let through infrared and radio waves. For most of human history, we couldn't see what was there. We knew there was something massive at the center because the stars near it were moving too fast, orbiting something invisible, but we didn't know what. Then, in the 1990s, astronomers began tracking individual stars near the galactic center with enough precision to map their orbits. One star, called S2, orbits the center once every 16 years in a stretched ellipse that brings it within 17 light hours of the center at closest approach. 17 light hours, that's about 3 times the distance from the Sun to Pluto. At that distance, S2 is moving at nearly 2% the speed of light. Nothing moves that fast unless it's orbiting something extraordinarily massive. The only object that fits the data is a black hole, not a stellar mass black hole left over from a supernova. A supermassive black hole, 4 million times the mass of the Sun. Sitting at the center of the Milky Way, holding the entire galaxy in its gravitational grip. They call it Sagittarius A star. It's quiet most of the time, not actively feeding, just sitting there pulling on the stars around it, warping space-time in a region so dense and so violent that any planet unlucky enough to form there would be sterilized by radiation and torn apart by tidal forces. The galactic center is not a place you visit, it's a place you avoid, and yet it's the anchor point for everything. The Sun orbits Sagittarius, a star, once every 230 million years, along with every other star in the disk, all of us caught in the same slow rotation around a black hole we will never see and can never escape. That's what holds the Milky Way together, not the stars, the black hole. The thing at the center that has already died, if it ever lived at all, because supermassive black holes don't form from stars, they're too big. They might have formed from direct collapse in the early universe, or from runaway mergers of smaller black holes, or from some process we haven't figured out yet. We don't know. What we do know is that every large galaxy has one. Every spiral, every elliptical, every galaxy big enough to have a core has a supermassive black hole at its center, and the mass of that black hole correlates with the mass of the galaxy's central bulge. The bigger the galaxy, the bigger the black hole. They grow together, they shape each other. The black hole pulls matter inward, the matter heats up, radiates, blows gas out of the galaxy in winds and jets. The galaxy feeds the black hole. The black hole regulates the galaxy's growth. It's a feedback loop that's been running since galaxies first formed, and the result is that at the heart of nearly every galaxy in the universe, there is a dead region. A place where nothing can survive, nothing can orbit safely, nothing can exist except the black hole and the doomed matter spiraling into it. The Milky Way is one galaxy, one structure, 100,000 light-years across, 1,000 light-years thick, home to somewhere between 100 billion and 400 billion stars depending on the count. And buried inside it, invisible, scattered through the disk and the halo and drifting out into intergalactic space, are 100 billion remnants, dead stars, failed stars, collapsed cores and cooling embers. Objects that used to shine and no longer do, objects that used to burn and ran out of fuel, objects that exploded or faded or simply stopped. The galaxy you see is the bright part, the part still alive. But the majority of its mass and the majority of its history belong to the parts that are finished, to the graveyard. And we live in the middle of it, on a planet made from the debris of earlier deaths, orbiting a star that will one day join the graveyard itself, looking up at a sky full of lights that are, every one of them, temporary. That's the Milky Way, that's home. A spiral structure rotating slowly around a supermassive black hole, filled with billions of stars in various stages of life and death, most of them too far away to ever visit, many of them already dead by the time their light reaches Earth, all of them caught in the same slow gravitational dance that's been running for 13 billion years and will keep running until the galaxy itself is torn apart or merged with another. And the Milky Way is not unique, it's not special, it's not even particularly large. It's one galaxy among trillions. And every one of those trillions has its own population of dead stars, its own graveyard, its own history written in the cooling remnants of suns that burned out long before anyone was around to see them. The Milky Way is full of ghosts, so is every other galaxy, so is the universe. And the space between galaxies, the voids where no stars burn and no planets form, those voids are larger and emptier and stranger than anything we've talked about so far. The Milky Way is not alone. That should be obvious. You look up and you see stars, thousands of them, if you're far enough from city lights, and those stars belong to our galaxy. But between the stars, In the dark patches, in the gaps where nothing seems to shine, there are other galaxies. Billions of them. Trillions, actually, according to the latest surveys. Each one a structure comparable to the Milky Way, containing tens or hundreds of billions of stars, scattered across distances so enormous that the word distance stops carrying useful information. The universe is not a single galaxy with empty space around it. It is a foam, a web, a three-dimensional network of galaxies strung along vast filaments, clustered into groups and superclusters, separated by voids so large and so empty that if you were somehow placed in the middle of one, you could look in every direction and see nothing, no stars, no galaxies, just darkness. The kind of darkness that makes interstellar space look crowded by comparison. 2 trillion galaxies. That is the current estimate, published in studies using data from the Hubble Space Telescope and later refined with observations from other instruments. 2 trillion observable galaxies within the bubble of space we can see, the region from which light has had time to reach Earth since the Big Bang. That number is almost certainly an undercount, because the farther you look, the fainter and smaller galaxies become, and at some point they drop below the detection threshold of even our best telescopes. There could be more, many more, but 2 trillion is the number we have, and it is large enough to break intuition. The Milky Way contains somewhere between 100 billion and 400 billion stars. Multiply that by 2 trillion galaxies, and you get a number so large that astronomers do not bother writing it out. They just say the universe contains more stars than grains of sand on every beach on Earth, which is true, and then they move on because there is no human experience that maps onto a number that size. You cannot picture 2 trillion galaxies the way you can picture 1,000 or even 1,000,000. The number exists as an abstraction, a piece of math that describes a structure too large to hold in your head all at once. And those galaxies are not scattered randomly. That is the part that took decades to figure out. For most of the 20th century, astronomers assumed the universe was more or less uniform on large scales. Galaxies were distributed evenly, like grains of sand in a bucket, with no particular pattern or structure beyond random clustering. That assumption turned out to be completely wrong. In the 1970s and 80s, as telescopes improved and survey projects began mapping the positions of thousands of galaxies in 3 dimensions, measuring not just where they appeared on the sky, but how far away they were, a pattern emerged. Galaxies were not evenly distributed. They were clustered, clumped into groups and chains and sheets, with enormous empty regions between them. The first major survey to reveal this structure was the CFA Redshift Survey, led by astronomers at the Harvard-Smithsonian Center for Astrophysics. In 1986, they published a map showing the positions of more than 1,000 galaxies within about 200 million light-years of Earth. The map looked nothing like a uniform distribution. It looked like a slice through a sponge. Dense regions where galaxies crowded together, separated by vast empty bubbles. The largest empty region in that survey, dubbed the Boots Void after the constellation where it appeared, was roughly 300 million light-years across and contained almost no galaxies at all. 300 million light-years of nearly empty space. A hole in the universe large enough that light takes 300 million years to cross it. That was just the beginning. Larger surveys followed. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey. Each one mapped more galaxies over larger volumes, and each one confirmed the same basic structure. The universe on large scales looks like a web. Galaxies are strung along thin filaments, vast threads of matter stretching across hundreds of millions of light-years. Where filaments intersect, you get clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. Clusters group into superclusters, even larger structures containing dozens of clusters spread across 1 billion light-years or more. And between the filaments, filling most of the volume of space, are the voids, regions where almost nothing exists. No galaxies, no stars, no gas, just the faint background radiation left over from the Big Bang and the occasional lonely galaxy that somehow ended up there by mistake. This structure has a name. Cosmologists call it the cosmic web. It is the largest pattern in the universe, the framework that organizes matter on scales far beyond individual galaxies or even clusters. And it is not random. It formed from tiny fluctuations in the density of matter in the early universe, variations that were imprinted during the first fraction of a second after the Big Bang. Those fluctuations were tiny, less than 1 part in 100,000, but they were enough. In regions that were slightly denser than average, gravity pulled matter inward. Those regions grew denser. In regions that were slightly less dense, matter drifted outward into the growing concentrations. Those regions became voids. Over billions of years, the pattern amplified. Dense regions collapsed into filaments and nodes. Voids expanded. The cosmic microwave background, the afterglow of the Big Bang, still carries the imprint of those early fluctuations. You can see them in the temperature map of the sky, faint hot and cold spots measuring differences of a few millionths of a degree. Those spots are the seeds, the blueprint. Zoom forward 13.8 billion years, and those seeds have grown into the cosmic web, a structure so large that it spans the entire observable universe. Here is what that structure looks like in numbers. The nearest large cluster of galaxies to the Milky Way is the Virgo cluster, sitting about 50 million light-years away. It contains somewhere around 1,500 galaxies, most of them smaller than the Milky Way, packed into a region roughly 15 million light-years across. 50 million light-years, that is roughly 500 times farther than Proxima Centauri, the nearest star. And the Virgo cluster is close. It is part of our local neighborhood, gravitationally linked to the Milky Way and the other galaxies in what astronomers call the local group. The local group itself is tiny by cosmic standards. It contains the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 80 smaller galaxies, all bound together in a region roughly 10 million light-years across. The Virgo cluster, much larger and more massive, sits at the center of an even larger structure called the Virgo supercluster, which contains several smaller clusters and groups spread across roughly 100 million light-years. The Milky Way is on the outer edge of that supercluster, part of a subfilament called the local sheet. But even the Virgo supercluster is not a fundamental unit. It is part of something bigger. In 2014, a team of astronomers, led by Brent Tully at the University of Hawaii, published a paper describing a structure they called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, a gravitationally connected region containing roughly 100,000 galaxies spread across 500 million light-years. The Milky Way sits near the outer edge, the center of mass, the point toward which everything in Laniakea is slowly being pulled, lies in the direction of the constellation Centaurus, about 250 million light-years away. That region, called the Great Attractor, is hidden behind the plane of the Milky Way, obscured by dust and gas, but its gravitational influence is unmistakable. Every galaxy in Laniakea, including ours, is drifting toward it at hundreds of kilometers per second. The drift is slow on human timescales, but inexorable on cosmic ones. Billions of years from now, the galaxies in Laniakea will have moved closer together, pulled inward by the combined gravity of the structure. Eventually, they may merge into a single enormous galaxy, or more likely, the expansion of the universe will tear the structure apart before that can happen. Either way, Laniakea is not permanent. It is a snapshot, a temporary arrangement of matter that exists because the universe is not old enough yet for expansion to have pulled everything apart. And Laniakea is one structure among many. The cosmic web contains thousands of superclusters, each one comparable in size, each one separated from its neighbors by voids. The largest void ever discovered, the KBC void, may be nearly 2 billion light-years across. 2 billion light-years. Light leaving one side of that void would take 2 billion years to reach the other side, and during that journey it would pass through almost nothing. A handful of galaxies scattered through the emptiness, isolated from each other by distances that make intergalactic travel look absurd even in science fiction. If you lived in a galaxy in the center of a supervoid like that, you would look up and see almost nothing. A few faint smudges scattered across the sky. No Milky Way, no bright band of stars cutting across the horizon, just darkness. You would have no way to know that the universe was full of galaxies unless you built telescopes powerful enough to see across the void, and even then, the galaxies you found would be so far away that their light had been traveling for 1 billion years before it reached you. You would be living in what looked like an empty universe, unaware that you were sitting in a hole, that most of the universe existed beyond the walls of your void, that you were isolated not by distance alone, but by structure, by the way matter organized itself in the aftermath of the Big Bang. This raises a question that cosmologists have started to take seriously. Could a civilization develop in a void galaxy and never realize the universe was full of other galaxies? The answer is yes, easily. If you are sitting in the middle of a supervoid, the nearest galaxy cluster could be 1 billion light-years away. The light from those galaxies would be stretched by cosmic expansion, redshifted so far into the infrared that it would be nearly invisible to optical telescopes. You would need extraordinarily sensitive instruments to detect it, and you would need to be looking in the right direction. If your civilization developed astronomy but never built infrared telescopes, or if your early instruments were not sensitive enough to pick up the faint glow of distant galaxies, you might conclude that your galaxy was the only one, that the universe was small, that you were alone. You would not be wrong because of bad science. You would be wrong because of bad luck, because you happened to be born in a region of space where the evidence for a larger universe was hidden beyond your detection threshold. This is not hypothetical. Our own history of cosmology is full of moments where we thought we understood the size of the universe and then discovered we were wildly underestimating it. In the early 1900s, the dominant view was that the Milky Way was the entire universe. The spiral nebulae scattered across the sky were thought to be clouds of gas within our galaxy, not separate galaxies at all. It took Edwin Hubble's observations in the 1920s, measuring the distance to the Andromeda galaxy using Cepheid variable stars, to prove that the nebulae were galaxies, that the universe was vastly larger than anyone had imagined. If Hubble had been born in a void galaxy, he might never have seen Andromeda. It might have been too faint, too far, beyond the reach of his telescope, and the scientific consensus would have remained that the Milky Way was all there was. We got lucky. We live in a relatively dense region of the cosmic web, close enough to other galaxies that we could detect them with early 20th century technology. A civilization in a void would not have that luck. The voids matter for another reason. They are growing. The universe is expanding, and the expansion is accelerating. driven by something cosmologists call dark energy. Dark energy makes up about 68% of the total mass energy content of the universe, and its effect is to push space itself apart. The denser regions of the universe, the filaments and clusters, are held together by gravity. Their galaxies are bound tightly enough that expansion does not pull them apart. But the voids are not gravitationally bound. There is nothing holding them together. So as space expands, the voids expand with it. They get larger, emptier. The galaxies at the edges of voids drift farther apart. The cosmic web, which looks like a sponge today, will look more and more thread-like as time goes on. The filaments will thin. The voids will dominate. Billions of years from now, a galaxy sitting in a void will be even more isolated than it is today, separated from its neighbors by distances that are growing faster than light can cross them. And because of the accelerating expansion, there will come a point where galaxies beyond a certain distance are receding so fast that their light will never reach us. They will cross what is called the cosmic event horizon, the boundary beyond which objects are forever out of reach. Once a galaxy crosses that horizon, it is gone, not destroyed, not collapsed, just gone, removed from the observable universe, lost to expansion. We will never see it again. We will never communicate with it. It will continue to exist, presumably, but it will exist in a part of the universe that is no longer causally connected to ours. This is already happening. The edge of the observable universe, the boundary defined by the distance light has traveled since the Big Bang, is currently about 46.5 billion light-years away. That is not the same as 13.8 billion light-years, the age of the universe, because space itself has been expanding while the light was traveling. The farthest galaxies we can see are not where they were when they emitted the light we are detecting. They have moved farther away, carried by expansion, and they are now much farther than 46.5 billion light-years. Some of them are already beyond the cosmic event horizon. We can still see them because the light they emitted in the past has not finished reaching us yet, but they are receding faster than the speed of light, and no signal we send today will ever catch up to them. They are gone. We are watching ghosts, fossils, light from galaxies that have already passed out of reach, frozen in time at the moment they crossed the horizon. The number of galaxies in the observable universe is shrinking. Not because galaxies are being destroyed, though some are merging and some are dying as their stars burn out, but because the boundary of what we can observe is closing in. Expansion is pulling distant galaxies over the horizon faster than new ones are coming into view. In the far future, trillions of years from now, if any civilizations still exist, they will look up and see far fewer galaxies than we see today. The Milky Way will have merged with Andromeda and several other members of the local group, forming a single large elliptical galaxy that astronomers have already nicknamed Milky Way. That galaxy will sit in an increasingly empty universe. The Virgo cluster will be gone, receded beyond the horizon. Laniakea will be gone. Most of the cosmic web will be gone. The sky will go dark. And any astronomers working in that distant era will look at their data and conclude correctly that the universe contains one galaxy, theirs. They will have no way to know that their universe was once full of galaxies, that the cosmic web once existed, that their galaxy was once part of a structure 500 million light-years across. The evidence will have been erased by expansion. The universe will have hidden its own history. This is the future we are building toward. Not collapse, not a big crunch, isolation. The universe is not going to end in fire. It is going to end in silence, in darkness, in a slow, cold fade as the galaxies drift apart and the stars burn out and the voids grow until there is nothing left but a few isolated islands of matter scattered through an ocean of expanding space, each one alone, unaware of the others, separated by distances so vast that even light cannot cross them. That is the trajectory. That is where the cosmic web is headed, and we are already watching it happen. Every distant galaxy we observe is a galaxy we will eventually lose. Every photon we detect from the edge of the observable universe is one of the last messages we will ever receive from that direction. The universe is giving us a finite window to see its full structure, and that window is closing. The 2 trillion galaxies are real. They exist. They are out there right now, scattered across the observable universe, organized into filaments and clusters and voids, each one containing billions of stars, many of those stars hosting planets, some of those planets almost certainly harboring life. The universe is not empty, it is full. Full of matter, full of structure, full of worlds, but it is also full of space. Vast stretches of emptiness that separate the galaxies and isolate them from each other, and that space is growing. The galaxies are not getting closer, they are getting farther apart. The cosmic web is stretching, the voids are expanding. And the universe, which looks so rich and so crowded when you count the galaxies, is mostly empty and getting emptier. That emptiness is the horror. Not that the universe is small, but that it is too large, too spread out, too full of distance and time, and the kind of isolation that makes even the idea of contact seem absurd. We live in a galaxy. That galaxy is part of a group. That group is part of a supercluster. That supercluster is part of a web. And that web is one small patch of a universe containing 2 trillion galaxies, most of which we will never see clearly, and many of which are already drifting out of reach. The universe is not set up for easy travel. It is not set up for conversation. It is not set up for meetings or exchanges, or the gradual accumulation of shared knowledge across civilizations. It is set up for isolation, for silence, for the slow, steady drift of matter into regions so far apart that causality itself breaks down. The cosmic web is a network only in structure. It is not a network in function. The galaxies are connected by gravity and history, but they are not connected by roads or signals or any mechanism that allows them to interact in real time. They are neighbors in the sense that they occupy the same universe, but they are separated by distances that make the word neighbor meaningless. And this is the universe we live in, not a single galaxy, not a cluster. A web of 2 trillion galaxies organized into a structure so large that it spans the entire observable universe, stitched together by gravity and dark matter, separated by voids that contain almost nothing. The Milky Way is one thread in that web, one small part of a structure that extends far beyond what we can see, far beyond what we can ever hope to explore. And every thread in the web is drifting farther from every other thread, pulled apart by the accelerating expansion that has been running since the Big Bang and will keep running until the universe is so spread out, so diluted, so empty that the only things left are isolated galaxies sitting in the dark, surrounded by voids that have grown large enough to swallow everything. The cosmic web is not permanent. It is a phase, a temporary configuration that exists because the universe is young enough and dense enough that structure can still hold together. In the deep future, the web will be gone, the voids will have won, and the universe will look the way it was always going to look eventually: empty, dark, quiet. The 2 trillion galaxies will still exist, but they will be alone, scattered through a volume of space so enormous that the light from one will never reach another, each one an island, each one a universe unto itself, unaware of the others, unable to communicate, isolated by the very structure of space-time. That is the end game. That is where expansion leads, and it is already underway. The universe is running away from us, not metaphorically, not in some poetic sense that makes for good television. Literally, measurably. Right now, at this moment, the vast majority of galaxies in the observable universe are receding from the Milky Way at speeds that increase with distance. The farther away a galaxy is, the faster it is moving away from us. And past a certain distance, galaxies are receding faster than the speed of light, which means we will never, under any circumstances, reach them. We will never communicate with them. We will never even see what they look like today. We are watching them as they were billions of years ago, and the light showing us that ancient image is the last light from those galaxies that will ever reach Earth. They are already gone, lost to a horizon that is closing in around us, shrinking the observable universe year by year, galaxy by galaxy, until eventually we will be alone. This is not a problem we can solve. It is not a limitation of our technology or our understanding. It is a structural feature of the universe itself, written into the equations that describe how space behaves, and it was not always obvious. For most of human history, the universe was assumed to be static, eternal, unchanging. The stars and galaxies sat where they were, fixed in place, neither approaching nor receding. That picture was simple, and it was wrong. The first crack in that picture came in the 1920s when Edwin Hubble, working at the Mount Wilson Observatory in California, measured the distances to a number of nearby galaxies and compared those distances to their velocities. He used Cepheid variable stars, pulsating stars whose brightness fluctuates at a rate tied to their true luminosity, to calculate how far away the galaxies were. Then he looked at their spectra, the light broken into its component wavelengths, and he noticed something strange. The spectral lines were shifted toward the red end of the spectrum. Redshift, the same effect you hear when a train whistle drops in pitch as the train moves away from you. Doppler shift, but for light. A galaxy moving away from you has its light stretched, shifted toward longer, redder wavelengths. A galaxy moving toward you has its light compressed, shifted toward shorter, bluer wavelengths. Most of the galaxies Hubble looked at were redshifted. They were moving away. That by itself was not shocking. Galaxies move. They orbit each other. They fall into clusters. They drift through space under the influence of gravity. What was shocking was the pattern. The farther away a galaxy was, the more redshifted it was. The more redshifted it was, the faster it was moving. Distance and velocity were proportional. Double the distance and you doubled the recession speed. That relationship, now called Hubble's law, was not something you would expect if galaxies were just wandering around randomly. It was something you would expect if space itself was expanding. If the fabric of the universe was stretching, carrying galaxies along with it, then galaxies farther away would be carried away faster because there was more space between us and them to stretch. Hubble published his results in 1929, and the static universe died, not immediately. Some physicists resisted. Albert Einstein himself had assumed the universe was static and had added a term to his equations, the cosmological constant, specifically to prevent them from predicting expansion or contraction. When Hubble's data came in, Einstein reportedly called the cosmological constant his biggest blunder. The universe was not static, it was expanding, and if it was expanding now, that meant it had been smaller in the past. Run the clock backward, and everything in the universe, all the matter, all the energy, all the space, converges on a single point, the Big Bang, the moment the universe began. For decades after Hubble, the assumption was that expansion was slowing down. Gravity pulls everything together. The galaxies are moving apart, yes, but they are also pulling on each other, and that pull should slow the expansion over time. The question was whether the slowdown was strong enough to eventually stop the expansion and reverse it, pulling everything back together in a big crunch, or whether the expansion would continue forever, just at an ever-decreasing rate. The answer depended on how much matter the universe contained. Too much matter and gravity wins. The universe collapses. Too little and expansion continues forever. Right on the edge, and you get a flat universe, one that expands forever but slows asymptotically towards zero velocity. Measuring the total mass of the universe turned out to be hard. Most of the mass is not in stars or gas. It is in dark matter, invisible material that does not emit light but exerts gravity. You can infer its presence by watching how galaxies rotate and how clusters move, but you cannot see it directly. And even with dark matter included, the numbers were coming in too low. The universe looked like it had only about 30% of the matter needed to stop the expansion. That pointed to eternal expansion. A slow, cold fade as the galaxies drifted apart and the stars burned out. Not the most dramatic ending, but at least it was an ending you could calculate. Then, in the late 1990s, two independent teams of astronomers set out to measure how fast the expansion was slowing down. They were using Type 1a supernovae, exploding stars that all reach roughly the same peak brightness, which makes them useful as distance markers. You measure how bright a supernova looks, compare it to how bright it should be, and you get the distance. You measure the redshift of the host galaxy, and you get the recession velocity. Plot distance against velocity for supernovae at different distances, different points in the history of the universe, and you can see how the expansion rate has changed over time. Both teams expected to find that expansion was slowing. That was the prediction. Gravity should be putting the brakes on. The data came back, and it said the opposite. Expansion was not slowing, it was speeding up. Distant supernovae, the ones whose light had been traveling for billions of years, were farther away than they should have been if the universe had been expanding at a constant rate, which meant the expansion rate had been slower in the past and had increased since then. The universe was accelerating. That result made no sense. Gravity is attractive. It pulls things together. It does not push them apart. If the expansion was accelerating, something else had to be driving it. Something that acted like a repulsive force, pushing space apart, overpowering the attractive pull of gravity. The cosmological constant, the term Einstein had added to his equations and later abandoned, suddenly became relevant again. Rename it, give it a new interpretation, call it dark energy, and it fit the data. Dark energy is not a thing. It is not a particle or a field in the traditional sense. It is a property of space itself. Every cubic meter of empty space contains a small amount of dark energy, and that energy has negative pressure. Negative pressure acts like repulsion. It pushes space apart. As the universe expands, more space is created, which means more dark energy, which means more repulsion, which means faster expansion. It is a runaway process. The more space you have, the faster it expands. And the acceleration has been going on for the last few billion years, roughly the second half of the universe's history. Early on, when the universe was smaller and denser, matter and radiation dominated. Gravity was strong enough to slow the expansion. But as the universe expanded and the density of matter dropped, dark energy started to take over. Today, dark energy makes up about 68% of the total energy content of the universe. Dark matter is about 27%. Ordinary matter, the stuff that makes up stars and planets and people, is less than 5%. We are a rounding error. The universe is dominated by things we cannot see and do not understand, and one of those things is actively tearing the universe apart. The discovery of dark energy won the Nobel Prize in Physics in 2011. It also introduced a problem that cosmologists are still trying to wrap their heads around. If expansion is accelerating, then there is a limit to how far we can see, not because our telescopes are not good enough, because the light from distant objects will never reach us. Space is expanding faster than light can cross it. That creates a boundary, a horizon, beyond which objects are permanently out of reach. This is not the same as the edge of the observable universe, though the two concepts are related. The observable universe is defined by how far light has traveled since the Big Bang. The universe is about 13.8 billion years old. Light has been traveling toward us for that long, but space has also been expanding during that time. So the objects that emitted the light we see today are now much farther away than 13.8 billion light-years. The current radius of the observable universe is about 46.5 billion light-years. That is how far away the most distant objects we can see are now, accounting for expansion. But the cosmic event horizon, the boundary beyond which objects are receding faster than light, is closer, much closer. About 16 billion light-years away in co-moving distance, the distance measured in terms of the current size of the universe rather than the light travel time. Here is what that means. Any galaxy currently sitting beyond the cosmic event horizon is receding from us faster than the speed of light. If we sent a light beam toward that galaxy today, the light would never reach it. The space between us and the galaxy is expanding faster than the light can travel through it. The light would make progress at first, moving away from us at 300 million meters per second, but the space it was traveling through would be stretching even faster, carrying the destination galaxy farther away. The light would keep moving forward, but the distance it needed to cover would keep growing. It would never close the gap. It would never arrive. And if light cannot reach a galaxy, neither can anything slower than light, which is everything with mass. Galaxies beyond the cosmic event horizon are lost, permanently, forever. We can still see some of them because the light they emitted in the past, when they were closer, before they crossed the horizon, is still reaching us. But that light is old. It shows us what those galaxies looked like billions of years ago, and it is the last light we will ever receive from them. Once that light finishes arriving, once the last photons from before they crossed the horizon reach Earth, those galaxies will disappear from view. They will fade from the sky, and we will have no way to know what happened to them, whether they are still there, still forming stars, still evolving, whether they developed life, whether they figured out what dark energy is. We will never know. They are on the other side of a horizon that we cannot cross, and they cannot cross, and nothing can cross. And the horizon is moving, not toward us, toward them, outward, because expansion is accelerating. Galaxies that are currently inside the horizon, galaxies we can still see, are drifting toward the edge, and eventually they will cross it. One by one, the galaxies in the observable universe will slip over the cosmic event horizon and vanish. The number of galaxies we can see is shrinking. Not because galaxies are being destroyed, though some are merging and some are dying, but because the space between us and them is expanding too fast. The observable universe is getting smaller. The sky is going dark. This process is slow. It takes billions of years. But it is happening, right now, tonight. The galaxies at the edge of the observable universe are fainter than they were a million years ago because the space between us and them has stretched, and the light has been redshifted farther into the infrared. A billion years from now, some of those galaxies will be invisible. 10 billion years from now, most of the distant galaxies will be gone. 100 billion years from now, the observable universe will be a fraction of its current size. The Milky Way will have merged with Andromeda and several nearby galaxies to form a single large elliptical galaxy. That galaxy will sit in an increasingly empty sky. The other members of our local supercluster, Laniakea, will have drifted beyond the horizon. The distant clusters, the cosmic web, the filaments and voids, all of it will be gone, vanished. Not because it ceased to exist, but because the light from it stopped reaching us. And in the far future, trillions of years from now, if any astronomers still exist, they will look up and see one galaxy, theirs. They will map the stars, study the dynamics, measure the expansion of space within their own galaxy, and they will conclude that the universe is one galaxy, that nothing exists beyond it. They will have no way to know that their universe was once full of galaxies, that the cosmic web existed. That expansion carried those galaxies away and erased the evidence. The history of the universe will have been deleted by the very process that created it. Expansion will have hidden its own past. That is the trajectory we are on. Not a dramatic ending, not a collapse or an explosion, just a slow, quiet fade into isolation. The accelerating expansion guarantees it. And it raises the question of what comes next. What happens after the galaxies disappear over the horizon? What happens when the observable universe contains only one galaxy and there is nothing left to see beyond it? The answer depends on what dark energy actually is and whether its strength remains constant. If dark energy stays the same, if the acceleration rate we measure today continues unchanged, then the universe expands forever. The galaxies drift apart, the stars burn out. The matter slowly decays or gets swallowed by black holes. The black holes evaporate via Hawking radiation over timescales so long that writing them out requires more zeros than fit on a page, and eventually the universe reaches a state called heat death, maximum entropy. No temperature differences, no energy gradients, no way to do work or sustain structure. Just a thin, cold, uniform soup of particles and radiation spreading through an ever-expanding space, forever. That scenario is called the Big Freeze. It is not violent, it is not sudden, it is just the end of everything that can happen because the universe has run out of ways to change. But there is another possibility, one that depends on whether dark energy gets stronger over time. If the density of dark energy increases as space expands, not just in total amount, but in energy per unit volume, then the acceleration does not just continue, it escalates. Expansion speeds up faster and faster until it becomes so rapid that it starts to tear things apart. Not just galaxies drifting away from each other, galaxies themselves ripped apart, stars pulled out of their orbits, planets stripped from their solar systems, eventually even atoms torn apart as the expansion of space overpowers the forces holding them together. That scenario is called the Big Rip. It is speculative. The current data does not support it strongly, but it is not ruled out. And if it happens fast, at least on cosmic timescales. Billions of years of gradual expansion followed by a final few million years where everything disintegrates. The Big Rip is the violent ending, the one where the universe does not just fade, it breaks. And there is no way to stop it because the force driving it is not a thing you can turn off or counteract. It is a property of space itself. If dark energy gets stronger, space rips. If it stays constant, space freezes. Either way, the universe ends, not in fire, not in collapse, but in emptiness, in silence, in a state where nothing can exist except the faint background hum of quantum fields that never quite go to zero. This is not a guess. It is a prediction based on the best data we have. The discovery of accelerating expansion, confirmed by multiple independent observations, by surveys of supernovae and measurements of the cosmic microwave background and studies of large-scale structure, all of it points to the same conclusion. The universe is not going to slow down. It is not going to stop. It is going to keep expanding faster and faster until almost everything in it is out of reach. The observable universe is not the universe. It is a bubble, a sphere of space centered on Earth, 46.5 billion light-years in radius, containing everything from which light has had time to reach us since the Big Bang. That bubble is not expanding, it is shrinking. The edge is moving inward because galaxies at the edge are crossing the cosmic event horizon. The farther away a galaxy is, the faster it is receding. At some distance, the recession speed equals the speed of light. That distance is the horizon. Galaxies beyond it are gone. Galaxies approaching it from the inside are fading. And the horizon is not a fixed distance. It is moving outward in co-moving terms, but the galaxies are moving outward faster, so relative to us, the horizon is closing in. Fewer and fewer galaxies remain inside it. The bubble is shrinking. The universe is getting smaller, from our perspective. Not because space is contracting, because space is expanding so fast that it is carrying the contents of the universe away from us faster than we can keep up. And we are not special. Every galaxy in the universe is experiencing the same thing. Every observer, anywhere, looking out at the cosmos, sees the same pattern. Distant galaxies receding, the expansion accelerating, the horizon closing in. The universe is isolating every observer from every other observer, carving the cosmos into separate bubbles that will eventually lose contact with each other. 100 billion years from now, an astronomer in a galaxy on the far side of the current observable universe will look up and see a different sky than we see. They will see galaxies that we cannot see because those galaxies are on their side of the horizon, and they will not see us. We will be on the other side of their horizon, out of reach, invisible. The universe is not one connected space that everyone shares. It is a collection of overlapping bubbles, and those bubbles are drifting apart. Eventually, they will stop overlapping. Every galaxy will be alone in its own bubble, unable to see or contact any other galaxy, separated not by distance alone, but by the structure of space-time itself. That is the future. That is what accelerating expansion leads to. Ultimate isolation. The discovery of dark energy did not just change cosmology, it changed the story of the universe. For a long time, the story was about origins. Where did the universe come from? How did it begin? What happened in the first few seconds? Those questions are still important, but they are not the whole story. The other half of the story is about endings. Where is the universe going? What is its fate? And the answer, according to the data, is that the universe is going nowhere. It is expanding into isolation. It is spreading itself so thin, so far apart, that eventually there will be nothing left but disconnected islands of matter drifting through voids that grow larger every second. The cosmic horizon is not a distant abstraction. It is a boundary that is closing around us, and everything beyond it is lost. Not destroyed, not collapsed, just lost, removed from our universe, still out there, presumably, but out of reach, gone. That is what the accelerating expansion means. It means most of the universe is already beyond our ability to ever interact with it. It means the 2 trillion galaxies we can see today are a temporary gift, a brief window where the universe is young enough and dense enough that light from distant objects can still reach us. That window is closing, slowly but inevitably. And once it closes, we will be left with a sky that contains only the galaxies in our immediate local group, the ones close enough that gravity holds them together against the expansion. Everything else will have vanished over the horizon. The Milky Way, or whatever it has become after merging with its neighbors, will sit alone in an empty universe, and any astronomers who come after us, any civilizations that arise billions of years from now, will look up and see nothing, no distant galaxies, no cosmic web, no evidence that the universe was ever full of light. They will think they are alone, and in every way that matters, they will be right. Which brings us to a different kind of silence, not the silence of empty space, though that is part of it, the silence of no signals, no messages, no sign of anyone else out there doing what we are doing, looking up, asking questions, building telescopes, trying to understand. The universe is enormous. It is full of galaxies and stars and planets, and as far as we can tell, it is also full of silence. We have been listening for decades. We have found nothing. No transmissions, no probes, no structures too large or too strange to be natural. Nothing. And the accelerating expansion makes that silence worse, because it means that even if there are civilizations out there, even if they are trying to contact us, there is a very real possibility that we will never hear from them, because they are too far away, because the space between us is expanding too fast, because the light carrying their message is being stretched and redshifted and delayed until it arrives so faint, so distorted, so late that we cannot recognize it as a signal at all. The cosmic horizon does not just limit how far we can see, it limits how far we can communicate, and if there are civilizations beyond that horizon, we will never know. They will never know about us. We could both be shouting into the void, and the void would swallow the sound before it ever reached the other side. The universe is old enough and large enough that it should be full of voices. That is the calculation. Run the numbers, and the conclusion is inescapable. 2 trillion galaxies, hundreds of billions of stars in each one, trillions of planets. A non-zero percentage of those planets sitting in habitable zones where liquid water can exist. A non-zero percentage of those planets with the right chemistry, the right atmosphere, the right conditions for life to start. A non-zero percentage of those planets where life survives long enough to evolve complexity, intelligence, technology. Even if you make the percentages tiny, even if you assume life is rare and intelligence is rarer and technological civilizations are rarer still, the universe is so large that the numbers add up. There should be someone out there, many someones, thousands of civilizations in our galaxy alone, millions across the observable universe, and some of them should be older than us, much older. Billions of years older, with billions of years to spread, to build, to send signals, to leave evidence. The galaxy should be crowded. The sky should be full of transmissions. There should be megastructures visible in telescope surveys, Dyson spheres harvesting the energy of entire stars, beacons flashing in patterns too regular to be natural, probes drifting through our solar system, ruins on nearby planets. Something, anything, evidence that we are not the first, not the only, not alone in a universe that has had 14 billion years to produce other minds. There is nothing, no signals, no probes, no structures, no ruins. The sky is full of stars and empty of voices. We have been listening since the 1960s, since the first searches for extraterrestrial intelligence pointed radio telescopes at nearby stars and scanned for narrowband signals that could only come from a transmitter. Project Ozma, run by Frank Drake at the Green Bank Observatory in 1960, listened to 2 stars, Tau Ceti and Epsilon Eridani, for a few weeks. It heard nothing. Searches have continued ever since, growing more sophisticated, covering more frequencies, listening to more stars. The SETI Institute. Breakthrough Listen. Dozens of independent projects, all of them scanning the sky for something artificial, something deliberate, something that says we are here. And the result, after more than 60 years of searching, is silence. Perfect, unbroken silence. The universe is not sending us messages. It is not even leaking radio noise the way Earth leaks radio noise. The faint crackle of television broadcasts and radar installations and cell towers that have been radiating into space since we invented the technology. If there are civilizations out there using radio, either they are too far away for us to detect, or they are not broadcasting in ways we can recognize, or they do not exist. Those are the options: distance, invisibility, or absence. None of them are comforting. The paradox has a name. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi asked a question that has been haunting astronomers ever since. Where is everybody? The context was a discussion about flying saucers, which were a popular topic in the 1950s, though Fermi was not asking about UFOs. He was asking something deeper. If intelligent life is common, and if it tends to develop spacefaring technology, and if it has had billions of years to spread across the galaxy, then where are the aliens? Why haven't we seen them? Why isn't the galaxy obviously full of their presence? Why does the Earth look untouched, uncontacted, alone? The question is simple. The implications are not. Because once you start thinking about it seriously, once you take the size of the galaxy and the age of the universe and the sheer number of opportunities for life to arise, the absence of evidence starts to look like evidence of something. Not evidence that aliens definitely do not exist. Evidence that something is stopping them from being obvious. The Drake equation is the usual starting point. It was formulated by Frank Drake in 1961 as a way to estimate the number of detectable civilizations in the galaxy. It breaks the problem into factors: the rate at which stars form, the fraction of stars with planets, the number of planets per star that could support life, the fraction of those planets where life actually arises, the fraction of those where life becomes intelligent, the fraction where intelligence develops technology capable of interstellar communication, and the length of time such civilizations remain detectable. Multiply those factors together and you get a number. The number of civilizations we should be able to detect right now. The problem is that most of those factors are unknown. We have decent estimates for the first few: star formation rates, planetary abundance, habitable zones, but the biological and sociological factors, the ones that determine how often life starts and how often it becomes intelligent and how long it lasts, those are guesses. Educated guesses in some cases, wild speculation in others. Plug in optimistic numbers and you get thousands of civilizations in the galaxy. Plug in pessimistic numbers and you get less than one. We might be it. The equation does not tell you the answer. It tells you what you need to know to find the answer, and we do not know it yet. Robin Hanson, an economist and researcher, proposed one of the most unsettling explanations for the silence in the mid-1990s. He called it the Great Filter. The idea is straightforward. The path from a sterile planet to a galaxy-spanning civilization requires passing through a series of steps. Each step has a probability. Some steps are easy, some are hard, and at least one step, somewhere along the path, is so improbably difficult that almost no one makes it through. That step is the filter. It is the bottleneck, the barrier that prevents the galaxy from filling up with life. Hansen outlined 9 major steps. Start with a habitable star system. Move to simple replicating molecules. move to prokaryotic single-celled life, then eukaryotic cells with complex internal structure, then multicellular organisms, then tool-using animals with complex brains. Then a civilization capable of explosive technological growth, then colonization of the home star system, then expansion across the galaxy. Somewhere in that sequence, there is a filter, a step so difficult that it eliminates almost everyone who tries. The question is where? If the filter is early, if it is in the jump from chemistry to biology, or from simple cells to complex cells, then the hard part is behind us. Earth passed it. We got lucky. Life is rare, intelligence is rarer, but once you exist, the road ahead might be relatively clear. That is the optimistic interpretation. It means the galaxy is empty not because civilizations destroy themselves, but because they never form in the first place. Life is hard to start. The universe is full of sterile planets where nothing ever happened, where the chemistry never clicked, where the conditions were close but not close enough. Earth is special, rare, and if we survive the next few thousand years without killing ourselves, we might be one of the only civilizations to ever make it through. That scenario is lonely, but it is survivable. It means the future is open, the galaxy is empty, and we can fill it if we last long enough. But if the filter is ahead of us, if the hard part is not the origin of life, but the survival of technological civilizations, then we are in trouble, because it means something happens to almost every species that reaches our level of development, something that stops them, wipes them out, prevents them from spreading. Self-destruction is the obvious candidate. Nuclear war, ecological collapse, runaway artificial intelligence, biological weapons, climate change, resource depletion. The list of ways a technological civilization can destroy itself is long, and most of them involve technologies we either have now or are close to developing. The fact that we have not detected other civilizations might mean that civilizations do not last. They burn bright for a few centuries, maybe a millennium, and then they collapse or exterminate themselves before they can build interstellar ships or send out probes or leave marks visible across the galaxy. If that is the filter, if that is the step that almost no one passes, then the silence is not mysterious. It is a warning. It means we are approaching the barrier, the thing that killed everyone else, and we have no reason to think we will do better than they did. Hansen's argument is statistical. If life were easy and intelligence were common and survival were likely, the galaxy should look crowded. It does not. Therefore, at least one of those steps is not easy. The great filter exists. We do not know where it is, but the silence implies it is real. Every time we discover something that makes one of the early steps look easier, that updates the probability that the filter is ahead of us. When we find evidence that planets are common, that shifts the odds. When we find organic molecules in interstellar clouds, that shifts the odds. When we find liquid water on multiple moons in our own solar system, that shifts the odds. Every discovery that makes the universe look more hospitable to life makes the absence of life more disturbing, because it means the bottleneck is not in the raw materials or the opportunities. It is in something else, something we have not identified yet, something we might be about to encounter. There are other explanations, other proposed solutions to the Fermi paradox that do not involve a filter. One is the rare Earth hypothesis, which argues that while simple life might be common, complex life is not. The conditions that allowed multicellular organisms to evolve on Earth, stable climate, a large moon to stabilize axial tilt, plate tectonics to recycle carbon, a magnetic field to shield against radiation, a gas giant in the outer system to deflect asteroids, might be so specific and so rare that most planets never get past bacteria. Life exists, but it stays simple. Microbes, maybe algae, nothing with a nervous system. That would explain the silence. Intelligence requires complexity, and complexity requires conditions that are much rarer than we assumed. Earth is not just rare because life started here. It is rare because life survived long enough and stayed stable enough to build ecosystems complex enough to produce animals. Most planets do not get that far. They are sterile, or they are covered in microbes that never evolve into anything more interesting. The galaxy is full of bacterial mats and empty of minds. Another explanation is the zoo hypothesis, the idea that advanced civilizations exist, but they are deliberately avoiding contact with us. Maybe they have ethics. Maybe there is a galactic protocol, a rule that says you do not interfere with younger civilizations until they reach a certain level of development. We are in a zoo or a nature preserve, being watched but not contacted, left alone to see whether we make it on our own. This explanation is popular in science fiction and deeply unsatisfying as science because it is unfalsifiable. You cannot disprove the claim that aliens are hiding. If they are good at hiding, you would not see them. The absence of evidence becomes evidence for the hypothesis, which is not how science is supposed to work, and it requires a level of coordination and restraint that seems implausible. One breakaway faction, one curious scientist, one malfunctioning probe, and the silence breaks. The fact that it has not broken suggests either no one is there or no one cares enough to try. A third explanation is that they are here, but we are not recognizing them. Maybe intelligence does not build radio transmitters. Maybe advanced civilizations move beyond electromagnetic communication into something we do not have sensors for. Quantum entanglement, gravitational waves, neutrino beams, something exotic that does not show up in a radio survey. Or maybe they exist at scales we do not notice. Upnutted minds living in virtual environments, computronium scattered through the asteroid belts of a billion star systems, too small and too efficient to detect at interstellar distances. Or maybe they are so different from us that we would not recognize them as alive. Maybe intelligence can exist in forms that do not build cities or send signals, forms that operate on timescales too slow or too fast for us to perceive. A civilization that thinks one thought per century. A distributed intelligence spread across light years, communicating so slowly that we would not notice the pattern. This is speculation, untestable and borderline unfalsifiable, but it is not impossible. We assume intelligence looks like us, builds like us, wants the same things we want: exploration, expansion, communication. Maybe that assumption is wrong. Maybe the universe is full of minds and we are looking for the wrong signatures. Or maybe they destroy themselves, not in a single catastrophic event, but slowly, gradually. Civilizations rise, develop technology, exhaust their resources, destabilize their environments, and collapse back into pre-industrial states. They do not go extinct. They just lose the ability to send signals, to build rockets, to sustain the kind of infrastructure that makes them visible across interstellar distances. The galaxy might be full of post-collapse civilizations, scattered remnants of species that reached our level once and then fell. They are still there, still alive, but they are not building telescopes anymore. They are farming, surviving, trying to rebuild if they remember what they lost. That would explain the silence without requiring extinction. It just requires failure, repeated failure. Civilizations that cannot sustain themselves, cannot stabilize, cannot make the jump from planetary to interstellar. They keep trying and they keep falling, and the galaxy stays quiet because no one lasts long enough to shout. The timing matters. Humans have been industrial for about 200 years. We have been using radio for about a century. Signals from Earth have spread outward at the speed of light in a growing sphere, currently about 100 light-years in radius. That sphere contains a few thousand stars. If there is a civilization within that sphere capable of detecting our signals and interested enough to respond, we would not hear back for decades at minimum. A signal sent today to a star 50 light-years away would not receive a reply for 100 years, 50 for the signal to get there and 50 for the response to come back. Interstellar communication is slow. Even if someone is listening, even if they respond immediately, the conversation happens on timescales longer than human lifetimes. You send a message and your grandchildren get the reply, if you are lucky. That delay makes contact fragile. It requires patience, long-term stability, institutions that last for centuries, civilizations that do not collapse or lose interest or redirect resources before the reply arrives. How many civilizations have that kind of patience? How many would keep listening, keep transmitting, for the decades or centuries it takes to confirm that someone else is out there? We have been doing it for 60 years, and funding for SETI projects is always precarious. Governments lose interest, budgets get cut, private funding fills the gap, but it is not guaranteed. If we stopped listening tomorrow, if every radio telescope on Earth shut down, would anyone out there notice? Would anyone care? The Great Silence is not just an absence of signals, it is an absence of anything. No megastructures, no obvious terraforming projects, no Dyson spheres dimming stars as they harvest energy, no probes in our solar system that we can identify as artificial. We have mapped most of the large objects in near-Earth space. We have sent spacecraft to every planet. We have landed on asteroids and comets. We have rovers on Mars, landers on Titan, orbiters around Jupiter and Saturn. We have looked. We have not found anything that does not belong. No buried artifacts, no ancient installations, no relics from a previous visitor. The solar system looks untouched, natural, as if no one has ever been here before us. That is strange if the galaxy is old and civilizations are common. Because even if they are rare, even if only 1 in a million star systems produces a technological species, the ones that do should spread. If you can cross interstellar space at all, even slowly, even with generation ships that take thousands of years to reach the next star, you can colonize the galaxy given enough time. Send out 10 ships, let them settle 10 systems, let each of those send out 10 more. The growth is exponential. Within a few million years, even at sublight speeds, you have reached every star in the galaxy. A few million years is nothing on cosmic timescales. The Milky Way is billions of years old. If anyone started expanding even a billion years ago, they should be everywhere by now, and they are not. Or if they are hiding so well that we cannot see them. Either way, the silence holds. One of the most disturbing possibilities is that we are early. The universe is 13.8 billion years old, but stars capable of supporting life, stars with enough heavy elements to form rocky planets with atmospheres, only started appearing a few billion years ago. The first generations of stars were pure hydrogen and helium. They could not form planets like Earth. They had to live, die, explode, and enrich the interstellar medium with carbon and oxygen and iron before the next generation of stars could form worlds where chemistry could do interesting things. That process took time, billions of years. The Sun is a relatively late star, formed about 4.5 billion years ago from gas that had already been through multiple cycles of stellar birth and death. Life on Earth started relatively quickly after the planet cooled, within the first billion years, but it took another 3 billion years to evolve multicellular organisms and another 500 million to produce anything resembling intelligence. Add it up and you get a timeline where intelligent life could not have appeared much earlier than it did on Earth. Maybe we are one of the first. Maybe the galaxy is not full of ancient civilizations because there has not been enough time for ancient civilizations to arise. The universe had to age, stars had to die, planets had to form, life had to start and evolve, and all of that takes time. If we are in the first wave, if we are among the earliest species to reach this point, then the silence makes sense. There is no one to hear from yet. They are still evolving, still building, still figuring out fire and writing and electricity. And by the time they reach the stars, we might already be gone. That brings us back to the filter. If it is ahead of us, if the silence is because no one survives, then what kills them? What is the step that almost no one passes? The obvious answer is technology. The same tools that let you build rockets and computers and nuclear reactors also let you build weapons, bombs, biological agents, self-replicating machines that malfunction. We have come close to nuclear war multiple times. The Cuban Missile Crisis in 1962, the false alarm incidents during the Cold War, when radar glitches or software errors almost triggered launches. Stanislav Petrov, in 1983, the Soviet officer who chose not to report a missile detection that turned out to be a sensor error, preventing what might have been a retaliatory strike and a full-scale nuclear exchange. We survived those moments by luck as much as judgment. One different decision, one malfunction at the wrong time, and the outcome changes. Cities burn, infrastructure collapses, civilization breaks. Maybe we recover, maybe we do not. The filter does not require extinction. It just requires that you never reach the stars, that you never spread, that you stay confined to one planet until something goes wrong. Climate change is another candidate. Industrial civilization pumps carbon into the atmosphere warms, ice melts, sea levels rise, weather patterns shift, agricultural zones move, coastal cities flood, resource wars start, mass migrations destabilize governments. The process is slow enough that it is hard to see as an immediate threat, but fast enough that stopping it requires coordinated action on a global scale, and we are not good at that. We are barely managing it now, with full knowledge of what is happening and access to the technology to mitigate it. Imagine a civilization slightly less lucky, slightly less coordinated, or slightly more dependent on fossil fuels. They tip the balance. The planet warms past the point where their food systems can adapt. Ecosystems collapse. Population crashes. They do not go extinct, but they never build starships. The filter does not have to be dramatic. It can be a slow, grinding decline that leaves you alive but stuck. Or maybe it is something we have not thought of. A risk we do not see yet because we have not developed the technology that creates it. Nanotechnology that gets out of control. Artificial intelligence that optimizes for the wrong goal. Genetic engineering that introduces a vulnerability we do not notice until it is too late. Every new capability is also a new failure mode. The more powerful your tools, the more damage you can do with a mistake. And mistakes happen. Systems fail. People make bad decisions under pressure. Accidents cascade. One malfunctioning machine, one misaligned optimization function, one engineered virus that mutates. The filter might not be a single event. It might be a probability curve. The longer you stay at high technology, the more chances you have to roll the dice and lose. That is the nightmare scenario. that the great filter is not behind us, that we have not passed it yet, that every species that reaches our level faces the same challenge and almost all of them fail. The galaxy is quiet because intelligence is suicidal, because the same traits that let you build civilization, curiosity, tool use, the ability to reshape your environment, also make you dangerous to yourself. You reach a certain level of power and you do not have the wisdom to use it safely. You build weapons you cannot unuse. You alter systems you do not fully understand. You move faster than your institutions can adapt, and eventually something breaks. Not everywhere, not all at once, but often enough that the galaxy stays empty, often enough that the odds are against us. That is what the silence might mean, that we are next, that the filter is waiting. That every year we survive without catastrophe is another year we got lucky, and luck does not last forever. The alternative is worse, that the filter is not ahead of us, that we have already passed it. That life is so improbably rare that the jump from chemistry to biology, or from prokaryotes to eukaryotes, or from single cells to multicellular organisms is so difficult that Earth is one of the only places it has ever happened. The galaxy is full of planets, trillions of them, and every single one is sterile. Rocks and ice and atmospheres with no one to breathe them. We are alone, completely. The only minds in the galaxy. Maybe the only minds in the universe. That silence is not a warning. It is a fact, a description of reality. And it means there is no one out there to meet, no one to talk to, no one to learn from, no older civilizations with answers to the questions we are asking. No cosmic community waiting for us to join once we figure out faster than light travel or crack the code of interstellar communication. Just us, one species, one planet, one fragile bubble of awareness in an ocean of dead matter. The universe is not hostile, it is indifferent. It does not care whether we survive, it does not care whether we spread, it does not care whether we exist at all. And if we disappear, if we join the silence, nothing will notice. The stars will keep burning. The galaxies will keep drifting apart. The universe will continue exactly as it would have if we had never been here. That realization, that sense of scale and insignificance is its own kind of terror. Not the fear of being destroyed, the fear of never having mattered in the first place. The universe does not hate you. That would require it to notice you exist. It does not love you. It does not care about you. It does not have opinions about your choices, or your civilization, or your planet, or the star you orbit. It is not watching. It is not judging. It is not waiting to see whether you succeed or fail. The universe is not a parent, not a teacher, not a god, not an observer. It is a collection of physical processes operating according to laws that do not include a term for human importance. You are made of atoms that follow those laws. Your planet follows those laws. Your star follows those laws. And nothing in those laws says you matter. That is not cruelty. It is not punishment. It is not even indifference in the emotional sense, the way a person might be indifferent to something they have chosen to ignore. The universe is not choosing, it is just running, following its equations, expanding, cooling, organizing matter into structures that form and dissolve over timescales that make your entire species look like a flicker. The terror is not that the universe is hostile. The terror is that it is exactly as indifferent as the equations say it should be, and understanding that, really understanding it, strips away the last comfortable illusion that you are here for a reason the cosmos would recognize. For most of human history, we did not have to think about this. The universe was small. The Earth was the center. The stars were lights on a sphere that rotated around us. The sun and moon and planets moved through the sky in patterns we could predict, and those patterns mattered because they were about us. Astrology, the idea that the positions of celestial objects influence human affairs, only makes sense if you think the cosmos is paying attention. It requires a universe that cares where Mars is when you are born, a universe that organizes itself around human concerns. That universe is gone. It was never real, but for thousands of years we thought it was, and that belief made the sky feel connected to us, personal, relevant. Then Copernicus moved the Earth out of the center. Galileo pointed a telescope at Jupiter and saw moons orbiting something other than Earth, proving we were not the only center of motion. Newton wrote down the laws that govern how objects move, and those laws applied equally to apples and planets. No special cases, no exceptions for things that mattered to humans. The sky stopped being about us. It became a system, a set of objects following rules. The rules were beautiful, elegant, predictive, but they were not written for us. They did not care whether we understood them or not. Then the universe got bigger, a lot bigger. In the 1700s, astronomers assumed the Milky Way was the entire universe, and it was big enough. Thousands of stars, maybe tens of thousands, scattered through a region of space we could measure in light years. Then William Herschel tried to map the Milky Way and realized it was vastly larger than anyone had guessed, a disk of stars stretching across thousands of light years. Then, in the early 1900s, the nebulae debate tried to settle whether the spiral nebulae scattered across the sky were clouds of gas within our galaxy, or separate galaxies far away. Edwin Hubble settled it in the 1920s by measuring the distance to Andromeda using Sepierhead variable stars. Andromeda was not a nebula, it was a galaxy. A structure comparable to the Milky Way, sitting nearly 1 million light-years away, completely separate, containing hundreds of billions of stars. And it was not alone. The sky was full of galaxies, thousands visible in surveys, then millions, then billions. The universe, which had felt large when it was one galaxy, suddenly became incomprehensibly vast, and every measurement, every new survey, every deeper telescope made it larger. The Hubble Space Telescope looked at a tiny patch of blank sky, a region the size of a grain of sand held at arm's length, and found 10,000 galaxies in that patch alone. The universe was not just big. It was so big that human intuition could not process the scale. You could say the numbers: 93 billion light-years across, 2 trillion galaxies, hundreds of billions of stars in each one. But saying the numbers did not make them feel real. They stayed abstract. Too large to fit inside a mind shaped by evolution to care about things within walking distance. The size alone is not the problem. The problem is what the size implies. If Earth is one planet among trillions, orbiting one star among hundreds of billions in one galaxy among 2 trillion galaxies, then Earth is not special. It is not central. It is not the point. It is a random patch of rock in a random solar system, in a random galaxy, no more significant than any other patch of rock anywhere else. You can argue that Earth is special because it has life, because it has you, because it is the only place we know of where anything interesting is happening. But that argument only works if you think life is rare, if you think intelligence is rare, if you think we are unusual. And the universe is so large that even if life is rare, even if intelligence is incredibly rare, there should still be billions of planets where it happened. We have not found them yet, which either means we are even more rare than we thought, in which case the universe is almost entirely dead and we are a statistical fluke, or it means they are out there and we just have not seen them, in which case we are not special at all. Either answer is uncomfortable. Either we are alone in a universe that is mostly empty, which makes us seem fragile and temporary, or we are common in a universe that is full of others like us, which makes us seem replaceable. The scale of the universe does not leave room for Earth to be important in any cosmic sense. It leaves room for Earth to be typical. One more planet in a distribution so large that individual planets do not register as significant. And it gets worse, because the universe is not just large, it is also old, 13.8 billion years. That is the current estimate, based on measurements of the cosmic microwave background, the faint radiation left over from when the universe was 380,000 years old and still glowing from the heat of the Big Bang. 13.8 billion years is a timescale that makes human history invisible. Civilization has existed for about 10,000 years if you are generous with the definition. Anatomically, modern humans have existed for about 300,000 years. The genus Homo, the group that includes all human species, has been around for about 2.5 million years. All of that, every human ancestor, every stone tool, every cave painting, every city, every war, every discovery, fits into the last 1/10% of the age of the universe. Zoom out a little further, and it disappears completely. The Sun is 4.5 billion years old. It is middle-aged. It has roughly another 5 billion years of stable hydrogen burning ahead of it before it expands into a red giant and swallows the inner planets. When that happens, assuming humans still exist, we will have to leave. The Earth will not be habitable. The Sun will not care. It will keep burning, following the same fusion equations it has been following since it ignited, indifferent to whether anything was alive on the planets that used to orbit in the habitable zone. 5 billion years from now, the Sun becomes uninhabitable. 10 billion years from now, it is a white dwarf, a cooling ember radiating away the last of its heat. 1 trillion years from now, it is a black dwarf, cold and dark, drifting through a galaxy that has long since stopped forming new stars. And the universe will keep going. The stars will die. The galaxies will drift apart. The black holes will evaporate. And eventually, trillions of years in the future, the universe will reach a state where nothing interesting can happen anymore because there is no energy left to drive change. Heat, death, maximum entropy, the end of everything that can end, and none of that cares whether you were here. This is the part that breaks people when they think about it seriously. Not the size, not the age, the indifference. The universe does not recognize your existence. It does not have a mechanism for noticing you. You are not written into the equations. The laws of physics describe how matter and energy behave under various conditions, and those laws produce stars and galaxies and planets, and, on at least one planet, life. But life is not a separate category in the equations. It is not a special case. It is chemistry. Complex chemistry, self-replicating chemistry, chemistry that builds structures and processes information and responds to its environment, but still chemistry. The same carbon atoms that form the proteins in your cells also form the carbon dioxide in the atmosphere, and the graphite in your pencil, and the diamonds buried in the Earth's mantle. The atoms do not know the difference. They follow the same rules in all contexts. Your body is a temporary arrangement of those atoms, held together by chemical bonds that will eventually break. When you die, the atoms disperse. They get recycled. Some of them end up in the soil, some in the air, some in other organisms. The carbon that used to be part of you will be part of something else, and it will not remember. Atoms do not have memory. They do not have history. They just are, and they follow the rules, and the rules do not care what structure they were part of 5 minutes ago or 5 billion years ago. Humans need meaning. That is not optional. It is built into how we process the world. We are pattern recognition machines, shaped by evolution to look for causes, to assign agency, to build narratives that explain why things happen. When something moves, we assume someone moved it. When something breaks, we assume someone broke it. When something exists, we assume it exists for a reason. That tendency served us well in environments where most of the important threats and opportunities were other agents, other humans, predators, prey, things that had intentions and could be predicted by modeling their goals. But it does not serve us well when we try to understand the universe. Because the universe does not have intentions, it does not have goals, it does not do things for reasons, it just does things. Particles interact, fields fluctuate, forces push and pull. Stars form because gravity pulls gas together until it is dense enough to ignite fusion. Stars die because they run out of fuel and collapse. Galaxies collide because they were moving toward each other and gravity pulled them together. None of that happens because the universe wanted it to happen. It happens because the initial conditions and the laws of physics made it inevitable. The universe is deterministic, or at least statistically deterministic if you account for quantum mechanics. It follows rules. It does not follow purposes. That conflict between the human need for meaning and the apparent meaninglessness of the cosmos is old, older than science. Religion was one way to resolve it. If the universe was created by a god or gods, if it was designed, if there was a plan, then you could fit yourself into that plan. You mattered because the Creator said you mattered. Your life had purpose because it was part of a larger story, a story written by someone who cared about the outcome. That framework gave people a way to feel significant even when they understood they were small. You might be a peasant, you might be powerless, but you were part of a divine plan, and that made your suffering and your choices meaningful. Science did not set out to destroy that framework, but it did. Not by disproving the existence of gods, which is not something science can do. By showing that the framework was not necessary. You could explain how the universe worked without invoking a creator. You could explain how life arose without invoking a divine spark. You could explain human behavior without invoking a soul. The explanations were not complete. They are still not complete, but they were good enough to show that the universe operated according to natural laws, and those laws did not require or suggest the presence of an intelligence guiding them. That is where the terror comes in. Not when you first learn that the Earth is not the center of the universe. That is surprising, but you can absorb it. Not when you learn that the universe is old and large. That is overwhelming, but it is still just a fact, something you can write down and move on from. The terror comes when you realize that the size and the age and the laws all point to the same conclusion. You are not the point. Your species is not the point. Earth is not the point. There is no point. The universe is not a story. It is a process. It does not have a climax or a resolution. It does not have a moral. It does not care whether you learn the lesson or miss it, because there is no lesson. It just runs, and when you are gone, it will keep running. The stars will keep fusing hydrogen. The galaxies will keep drifting apart. The cosmic microwave background will keep cooling, and nothing about any of that will change because you are here. You will leave no mark on the universe that the universe will notice. Your entire civilization, if it lasts 1,000,000 years, which is far longer than any civilization has ever lasted, will be a blip. A brief moment of organized complexity in one tiny corner of one galaxy. A moment so short that it does not show up on the timeline unless you zoom in to scales far smaller than the universe operates on. This is not a new realization. People have been grappling with it since they started thinking seriously about cosmology. Blaise Pascal, the 17th century mathematician and philosopher, wrote about the terror of infinite space. The eternal silence of these infinite spaces frightens me. He was writing before we knew about galaxies, before we knew about the Big Bang, before we understood how large the universe actually was, and he was already frightened by the scale. He understood that if space went on forever, or even if it just went on far enough that you could not see the end, then human concerns started to look trivial. You could not be important in an infinite space. There was too much room for other things, too much emptiness, too much scale. The silence Pascal wrote about was the absence of response. He looked up at the stars, and they did not answer. They did not acknowledge him. They were just there, distant, unreachable, indifferent. That silence is still there. We have better telescopes now. We can see farther. We can measure more precisely, and the silence is louder. The universe has had 13.8 billion years to respond to us, and it has not. It does not send signals. It does not rearrange itself to make us feel welcome. It just expands, cools, follows its equations. Carl Sagan tried to frame this realization as humbling rather than terrifying. He called Earth a pale blue dot, a tiny pixel in a photograph taken by Voyager 1 from the edge of the solar system. Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Sagan's point was that the smallness should make us kinder, more careful, more aware of how precious and fragile we are. And maybe it does, for some people, but for others, the smallness is crushing. It is not comforting to know that everything you care about fits on a dot too small to see in a photograph of the solar system. It is not comforting to know that the photograph itself is a view of a region of space so tiny that it does not register on galactic scales. Zoom out to the Milky Way and the solar system disappears. Zoom out to the local group and the Milky Way is one galaxy among dozens. Zoom out to the observable universe, and the local group is invisible. Every zoom erases you a little more. Every increase in scale makes you smaller. And the universe does not stop. There is no maximum zoom where you suddenly become significant again. You just keep shrinking until you are too small to matter. Some people find this liberating. If nothing you do matters on a cosmic scale, then you are free to decide what matters on a human scale. You can build your own meaning, choose your own values, live according to principles you select, rather than principles handed down by a universe that does not care. That is existentialism, roughly. The idea that in the absence of inherent meaning, you create meaning through your choices. It is a workable philosophy. It has helped a lot of people, but it does not make the universe less indifferent. It just shifts the frame. Instead of looking for meaning in the cosmos, you look for it in yourself, in your relationships, in your projects. You accept that the universe is not going to validate you, and you stop asking it to. That works if you can do it. If you can hold in your mind the idea that your life is meaningful to you, even though it is meaningless to the universe. Not everyone can. Some people need the validation. They need to feel that their choices matter in some larger context, that they are contributing to something bigger than themselves, something that will last. And the universe does not offer that. It offers the opposite. It offers the certainty that nothing you build will last. Not your cities, not your species, not your planet, not your star, not your galaxy. Everything ends, everything decays. Everything gets ground down by entropy until there is nothing left but a thin, cold, uniform distribution of particles spreading through an ever-expanding space. That is the ultimate indifference. Not just that the universe does not care about you now, that it will erase every trace of you eventually. The stars will die, the galaxies will drift apart, the black holes will evaporate. And when the universe reaches heat death, when it reaches maximum entropy, when there is no energy left to drive any process, there will be no record that you existed, no fossils, no ruins, no light from Earth still traveling outward through space, because by that point, trillions of years from now, any light Earth ever emitted will have been absorbed or redshifted into undetectability. The cosmic microwave background will have cooled to near absolute zero. The universe will be dark, empty, silent, and it will stay that way forever, because there is no process that reverses entropy, no mechanism that reboots the universe and starts it over. This is the end state, the final configuration, a universe that has run out of things to do, and in that configuration you are not there. You were never there in any sense that the final state would recognize. You were a brief local decrease in entropy, a temporary flicker of organization in a universe that was always heading toward maximum disorder. You happened, you ended, the universe continued. This is not a philosophical thought experiment. It is the prediction of thermodynamics applied to cosmology. The equations are clear. The universe is expanding. The expansion is accelerating. Dark energy is pushing space apart faster than gravity can pull it back together. Eventually, the galaxies that are not gravitationally bound to each other will drift out of causal contact. The stars will burn out, the gas will be used up, no new stars will form. The white dwarfs and neutron stars and black holes that remain will slowly decay or evaporate over timescales so long that the current age of the universe is a rounding error. And when the last black hole evaporates, when the last particle decays, the universe will be empty. Not empty in the sense of having nothing in it, empty in the sense of having nothing interesting in it, no structure, no complexity, no processes that produce change, just a faint background of radiation and a scattering of particles so spread out that they might as well not exist. That is the future. That is where the arrow of time points. And everything that has ever happened, every thought, every discovery, every work of art, every moment of joy or suffering will be gone, not forgotten, because there will be no one left to forget, just gone, erased by time and entropy, and the universe will not notice. Understanding that, really sitting with it, is a form of terror that has nothing to do with monsters or danger or pain. It is the terror of irrelevance, of realizing that you are not part of a story the universe is telling, because the universe is not telling a story, it is just running, and you are a side effect. A temporary eddy in the flow of energy from high concentrations to low, a brief complicated pattern in a process that is fundamentally about simplification. The universe started in a low entropy state, hot and dense and uniform, and it has been spreading out and cooling down and becoming more disordered ever since. You are part of that process. You are made possible by the fact that the universe is not at equilibrium yet, that there is still energy flowing from hot regions to cold regions, still gradients that can be exploited, still opportunities for complexity to arise, but you are not the goal. You are not the product. You are not what the universe was trying to make. You are what happens along the way, while the universe moves from order to disorder. And when the process is complete, when equilibrium is reached, you will not be possible anymore. The conditions that allow you to exist are temporary. They are an early universe phenomenon, a phase, and that phase is ending. That is the indifference, not that the universe dislikes you, that it does not have a category for you. You do not appear in the final state. You do not appear in the initial state. You appear in the middle, briefly, as a fluctuation, and then you are gone. The universe before you was the same universe after you. The laws did not change, the trajectory did not shift. You happened, and it made no difference to the equations. That is what it means to live in an indifferent cosmos. It means you are free to matter to yourself and to each other. It means you can build meaning within the bubble of your existence. But it also means the bubble is small and fragile and temporary, and when it pops, the universe will not remember it was there. You are not hated, you are not loved, you are not noticed. You are a pattern in the noise, briefly distinguishable from the background, and eventually you fade back into it. That is all. That is what we have learned by looking up, by measuring, by calculating, by following the evidence wherever it led. We learned that the universe is bigger than we thought, older than we thought, emptier than we thought, and less interested in us than we desperately wanted it to be. We learned that we are alone, or might as well be, in a cosmos that has no opinion about whether we survive. And we learned that understanding does not make it better, it makes it clearer. And clarity, in this case, is its own kind of horror. Not because the truth is complicated, because the truth is simple. The universe does not care. It never did, and nothing we do will ever change that. Yet here is the thing they do not tell you in the textbooks. The universe may not care, but you are part of the universe. You are made of it. The atoms in your body were forged in stars. The energy that powers your thoughts comes from the sun, filtered through a chain of biology that stretches back billions of years. You are not separate from the cosmos. You are a way the universe has organized itself, briefly, into something that can look back and ask why. That does not make you cosmically significant, but it does make you cosmically real. You are not an accident in the sense of being a mistake. You are an accident in the sense of being unplanned, but you are also an inevitability in the sense that, given enough time and enough planets, chemistry was always going to stumble into something like you. The universe is indifferent to whether you exist, but you exist anyway. And that existence, however brief, however insignificant on cosmic scales, is still a fact. Still something that happened, still a piece of the story, even if the story has no author and no ending and no point. You are here, right now, looking out at a universe that does not look back. And somehow, against all the emptiness and silence and scale, that act of looking, that moment of awareness, means something. Maybe not to the cosmos, but to you. And perhaps that is enough. Or perhaps it is not. Either way, the universe will not answer. It will just keep expanding, and you will keep looking up, searching for meaning in the stars, knowing they will never send it. But unable, despite everything, to look away. Here's the thing nobody tells you when you are standing in the dark, looking up at the stars. You are not just looking at the universe. The universe is looking at itself through you. Every photon that left a distant galaxy billions of years ago and happened to land in your eye, every pattern your brain assembles from those scattered points of light, every question you ask about what you are seeing, that is the universe doing something it does almost nowhere else. It is noticing. It is paying attention. It is trying to figure itself out. You are not an observer standing outside the cosmos looking in. You are a piece of the cosmos that has organized itself into something capable of observation. The atoms in your body, the neurons firing in your brain, the electrical and chemical processes that produce the experience of looking up and feeling small, all of that is physics. All of that is matter and energy following the same laws that govern stars and galaxies and black holes. Which means when you understand something about the universe, when you measure the distance to Proxima Centauri, or calculate the age of the cosmos, or figure out what dark energy is doing. That is not a human achievement separate from nature. That is nature achieving something through you. The universe has built, out of its own material, a system complex enough to study itself. And as far as we know, as far as 60 years of searching and 13.8 billion years of cosmic history can tell us, it has done that exactly once, here, on this planet, in you. That is not the story we usually tell. The story we usually tell is about insignificance, about scale, about how small Earth is and how short our lives are and how little we matter in the grand scheme of things. And all of that is true. Cosmically speaking, you are irrelevant. The equations that describe the universe do not have a term for you. The stars do not care whether you exist. The galaxies will drift apart whether you understand why or not. But here is what that story misses. Significance is not the same thing as existence. You are insignificant to the universe in the sense that your presence or absence does not change its trajectory. But you are not insignificant to the act of understanding. You are essential to it. Because without you, without something like you, the universe is just a process. It runs, it expands, it cools. Stars form and die, galaxies collide, black holes evaporate. And none of it means anything because there is no one there to recognize the pattern, no one to ask why, no one to realize that the cosmic microwave background is the afterglow of the Big Bang, or that the redshift of distant galaxies implies accelerating expansion. The universe can exist without observers. It did for billions of years before life appeared on Earth, but it cannot be understood without them. Understanding requires a mind, and minds, as far as we know, are rare. Maybe vanishingly rare, maybe unique. You are not cosmically important, but you are cosmically necessary for the one thing the cosmos cannot do on its own. Notice that it is here. Consciousness is strange. That is not a poetic statement. It is a straightforward description of a problem that physics and neuroscience have not solved. You know you are conscious. You have experiences. You see colors, hear sounds, feel textures. You have thoughts that feel like yours, a continuous stream of internal experience that you call yourself. That experience, whatever it is produced by your brain. About 86 billion neurons, each one connected to thousands of others, firing in patterns that somehow generate the sensation of being you. We can measure the firing. We can map the connections. We can identify which regions of the brain are active when you see a face, or solve a math problem, or remember a conversation. But we cannot explain how those physical processes produce the subjective experience of what it feels like to see a face, or solve a problem, or remember. There is a gap between the mechanics and the experience, and no one has closed it. Philosophers call it the hard problem of consciousness. The easy problems are things like figuring out how sensory information gets processed, or how memory works, or how decisions get made. Those are hard in the sense that they require detailed research, but they are solvable. The hard problem is explaining why there is something it is like to be you, why the firing of neurons feels like anything at all, why you are not just a biological robot processing inputs and generating outputs without any internal experience of the process. We do not have an answer. We have theories. Some scientists think consciousness is an emergent property, something that arises when information processing becomes complex enough, the way wetness emerges from water molecules even though no individual molecule is wet. Some think it is a fundamental feature of the universe, something woven into the fabric of reality at the same level as space and time and mass. Some think it is an illusion, that the sensation of having a unified continuous self is just a story your brain tells itself, a useful fiction that helps coordinate behavior. None of those theories have been proven. None of them have been ruled out. Consciousness remains one of the biggest unsolved problems in science. But whatever it is, however it works, it is real in the sense that you are experiencing it right now. You are aware that you exist. You know you are reading these words. You have a sense of being a person, of having a past and a future, of making choices and having preferences. That self-awareness, that ability to reflect on your own existence, is what makes you different from a star or a galaxy or a black hole. Those things exist. They follow laws. They interact with their environment, but they do not know they exist. They do not look at themselves and ask what they are. You do. And that difference, that single weird feature of biology that produces subjective experience, is what makes the universe comprehensible, because comprehension requires someone to do the comprehending. Here is what you can do that the universe cannot do on its own. You can build models. You can take observations, patterns of light and motion and energy, and construct an explanation for why those patterns exist. You see the sun rise and set, and you build a model that says the Earth is rotating. You see the stars shift position over the course of the year, and you build a model that says the Earth is orbiting the sun. You measure the redshift of distant galaxies, and you build a model that says space is expanding. None of those models are obvious. The data does not come with an explanation attached. The photons that hit your telescope do not carry labels saying this is from a galaxy that is receding at 70 kilometers per second per megaparsec. You have to infer that. You have to take the raw information and translate it into concepts, into mathematics, into a story about what is happening out there. And you have to check whether the story matches new observations, whether it predicts things you have not seen yet, whether it holds up when you push it to extremes. That process, the construction and testing of models, is how understanding happens. And it requires something the universe does not have: intent, curiosity, the desire to know what is true. The universe is not curious. It cannot be. Curiosity is a feature of minds, not of physical processes. Stars fuse hydrogen into helium because that is what happens when you compress hydrogen to high enough temperatures and pressures. They do not wonder why. Galaxies collide because they were moving toward each other, and gravity pulled them together. They do not ask what will happen next. Black holes evaporate via Hawking radiation because quantum field theory allows particle-antiparticle pairs to form at the event horizon, and occasionally one escapes. The black hole does not care whether you understand the mechanism. It just follows the equations. You are the only thing in this picture that asks why, the only thing that looks at a pattern and wants to explain it. The only thing that feels unsatisfied by not knowing. That curiosity, that drive to understand, is what makes you strange. It is also what makes you useful, because without it, the universe is just a machine running its program. With it, the universe becomes something that can study itself, that can recognize its own structure, that can write down the laws it is following and check whether they are correct. You are the universe's only feedback loop, the only part of it that can look at the whole and say, I see what you are doing, and you are good at it. That is the surprising part. Humans have only been doing science seriously for about 400 years. Before that, we had philosophy and mathematics and some careful observations, but we did not have the method. We did not have the idea that you should test your models against reality, that you should trust experiments over intuition, that you should discard theories that do not match the data, no matter how elegant they seem. That idea, the scientific method, is recent. Newton published the Principia in 1687. Darwin published On the Origin of Species in 1859. Einstein published general relativity in 1915. The cosmic microwave background was discovered in 1965. The accelerating expansion of the universe was confirmed in 1998. All of that, the entire structure of modern cosmology, was built in less than 4 centuries. 4 centuries out of 13.8 billion years. A blink. And in that blink, starting from almost nothing, knowing almost nothing, we figured out how old the universe is, how big it is, what it is made of, how it started, where it is going. We mapped the cosmic web. We measured the density of dark matter. We detected gravitational waves from colliding black holes. We sent probes to every planet in the solar system, and rovers to Mars, and a telescope into orbit that can see galaxies forming less than 1 billion years after the Big Bang. We did all of that with brains that evolved to hunt and gather on the African savanna. Brains that were shaped by natural selection to solve problems like finding food and avoiding predators and cooperating with other humans, not to understand quantum field theory or general relativity. And yet we can. We can take those Stone Age brains and train them to think about space-time and entropy and the wave function, and they work. Not perfectly, not without effort, but they work well enough that we can build models that match reality to astonishing precision. General relativity predicts the orbit of Mercury to within a few arcseconds. Quantum electrodynamics predicts the magnetic moment of the electron to 12 decimal places. The standard model of cosmology predicts the temperature fluctuations in the cosmic microwave background so accurately that the data and the theory are almost indistinguishable. Those are not approximations. Those are not lucky guesses. Those are deep matches between the math and the measurements, and they suggest that whatever consciousness is, whatever strange trick of biochemistry produces the experience of being you, it is powerful enough to decode the universe. That is what makes the anthropic principle interesting. The principle itself is simple. It says that the fact that we exist constrains what kind of universe we can be observing. If the universe were slightly different, if the physical constants had slightly different values, if the expansion rate after the Big Bang had been a little faster or a little slower, if the mass of the electron were different or the strength of the electromagnetic force were different, then atoms might not form, or stars might not ignite, or heavy elements might not be produced, or planets might not exist. And without planets, without stable environments, without liquid water and carbon and all the things that chemistry needs to build complexity, there would be no life, no observers, no one to ask why the universe has the properties it has. The fact that we are here asking the question means the universe must have properties compatible with our existence. That is the weak anthropic principle. It does not say the universe was designed for us. It says we could not have evolved in a universe that did not allow evolution. The selection effect is built in. We see a universe with these particular constants because those constants are the ones that permit observers to exist. If the constants were different, we would not be here to notice. The strong anthropic principle goes further. It suggests that the universe must have properties that allow observers to emerge at some point in its history. That version flirts with teleology, the idea that the universe has a purpose, and most physicists are uncomfortable with it. There is no evidence that the universe is trying to produce observers. It just happens to have properties that make observers possible, and we are the result. But even the weak version raises questions. Why does the universe have the constants it has? Why are they so finely balanced? If you change the strength of gravity by a tiny amount, stars do not form. If you change the mass of the down quark by a few percent, protons decay and atoms fall apart. If you change the cosmological constant by more than a factor of a few, The universe either recollapses before stars can form, or expands so fast that matter never clumps into galaxies. The range of values that allow a universe like ours, a universe with stars and planets and chemistry and time for evolution to run, is narrow. Not impossibly narrow, but narrow enough that it feels like a coincidence. And physicists do not like coincidences, they want explanations. One explanation is the multiverse. If there are many universes, each with different constants, then it is not surprising that we find ourselves in one of the rare ones where observers can exist. We could not exist in the others, the ones where gravity is too strong, or the cosmological constant is too large, or the electron is too heavy. Those universes are empty, or short-lived, or structureless. We do not see them because we are not in them. The multiverse does not explain why our universe has the constants it has. It just says that all possible constants exist somewhere, and we happen to be in a universe where the constants permit us. That explanation works logically. It removes the need for fine-tuning, but it is also untestable. If the other universes are truly separate, if there is no way to observe them or interact with them, then the multiverse is not a scientific theory. It is a philosophical idea. It might be true. It might be the correct explanation, but we cannot check, and that bothers some people. Science is supposed to deal with things you can test. The multiverse, by definition, contains regions you cannot test, so whether it counts as science or metaphysics depends on how generous you are with the definition. The other explanation is that we are missing something, that there is a deeper theory, some principle we have not discovered yet, that requires the constants to have the values they have. A theory of everything, if we ever find one, might explain why the electron has the mass it does, and why gravity has the strength it does, and why the cosmological constant is what it is. It might show that those values are not arbitrary, that they are determined by some underlying structure, some symmetry or constraint that makes the universe this way and no other way. If that is true, then the fine-tuning is not a coincidence, and it is not a selection effect. It is just physics. We do not understand the physics yet, but it is there, waiting to be discovered. That explanation is more satisfying to a lot of scientists because it suggests the universe is comprehensible all the way down, that there are no arbitrary starting points, that everything follows from something deeper. But we do not have that theory yet. We do not even know if it exists. And until we do, the fine-tuning remains a puzzle. Either way, the fact remains that the universe has the properties it has, and those properties allow you to exist. You are not a violation of the laws of physics. You are a consequence of them, a very complicated, very unlikely consequence, but a consequence nonetheless. The same forces that hold atoms together and make stars shine and drive galaxies apart also built your body and power your brain and produce the thoughts you are having right now. You are not separate from the cosmos. You are made of it. And that means when you look at the universe, when you measure it and model it and understand it, you are not an outsider studying a foreign object. You are part of the system studying itself. The universe, through you, has become self-aware. That is not a common occurrence. It might be the rarest thing the universe has ever done, and it is happening here, now, in you. That realization does not make you cosmically important. You are still a temporary arrangement of particles on a small planet orbiting an average star in an unremarkable galaxy. Your life is still brief. Your influence is still local. The universe will not remember you, but you are doing something the universe cannot do without you. You are noticing. You are asking why. You are building models and testing them and refining them and passing them on to the next generation so they can build better ones. That process, That accumulation of understanding is the only thing in the known universe that grows over time instead of decaying. Stars burn out, galaxies drift apart, entropy increases, but knowledge, if it is preserved, if it is shared, if it is built upon, knowledge grows. It is the one thing that moves in the opposite direction from the rest of the cosmos, and it only happens because you are here doing it. Carl Sagan put it like this: "We are a way for the cosmos to know itself." That is not mysticism. That is a literal description of what you are. The atoms in your body were made in stars. The energy powering your thoughts comes from the sun. The patterns your brain recognizes, the laws you write down, the equations you solve, all of that is the universe using a piece of itself to examine the rest of itself. You are the tool the cosmos built to understand its own structure. And the fact that you exist, the fact that you can look up and ask, where did this all come from, and how does it work, and where is it going? That is evidence that the universe is capable of producing systems complex enough to ask those questions. Whether it did so on purpose or by accident does not matter. The result is the same. You are here. You are aware. And that awareness is the rarest and strangest thing the universe has ever made. So here is where we are. The universe is vast. It is old. It is indifferent. It does not care about you. It does not have a purpose that includes you. It is not watching. It is not judging. It is not waiting to see whether you succeed, and nothing you do will change its trajectory. The stars will keep burning and dying. The galaxies will keep drifting apart. The expansion will keep accelerating. And billions of years from now, when the last stars have burned out, and the last black holes have evaporated, and the universe has reached a state where nothing interesting can happen anymore, there will be no record that you were here. You will be gone, forgotten, erased by time and entropy. That is the truth. That is what the equations say. That is the future you are building toward. But in the meantime, for this brief moment, while the universe is still young enough and structured enough that complexity can exist, you are here. You are noticing. You are asking questions. You are figuring things out. And that act, that strange, improbable act of a piece of the universe turning its attention inward and trying to understand the whole, that is the closest thing to meaning the cosmos has ever produced. It is not enough. It does not make you immortal. It does not make you significant on cosmic scales. It does not change the fact that the universe is indifferent, but it is something. It is the one thing you can do that stars cannot do, that galaxies cannot do, that black holes cannot do. You can look at the cosmos and recognize what it is. You can measure its age and its size and its contents. You can trace its history back to the Big Bang and project its future forward to heat death. You can write down the laws it follows and check whether they are correct. You can be wrong and revise your models and try again. You can build telescopes and accelerators and satellites. You can send probes to other worlds. You can take pictures of galaxies 13 billion light-years away and calculate what they looked like when the universe was young. You can do all of that, and when you do, you are not diminishing the cosmos. You are not making it smaller by understanding it. You are giving it something it did not have before. Witness, memory, comprehension. The universe has been running for 13.8 billion years without anyone noticing. And now, someone is noticing. That someone is you. And for as long as you are here, for as long as your species lasts, the universe is not just a process. It is a process that knows it is happening. That is the echo. Not your power, not your importance, your awareness, your ability to see the pattern, your refusal to stop asking why, even when the universe does not answer. That is the gift. That is the burden. That is the only thing about you that the universe has never done anywhere else, as far as we know. You are the exception, the anomaly, the place where the cosmos becomes conscious of itself, and that is worth something. Maybe not to the stars, maybe not to the galaxies, maybe not to the equations that describe how matter and energy behave, but to you. And maybe that is enough. Maybe it has to be, because the universe is not going to give you anything more. It is not going to validate you. It is not going to tell you that you matter. It is just going to keep expanding, keep cooling, keep following its laws. And you are going to keep looking up, keep asking questions, keep trying to understand, knowing the effort is temporary and the result is fragile, and the universe will outlast you by trillions of years. You will do it anyway, because you cannot help it. Because curiosity is built into you the same way gravity is built into space. Because you are a piece of the cosmos that has learned to ask what the cosmos is. And that question, however small, however brief, however irrelevant to the stars, is the most interesting thing the universe has ever done. It is doing it now, in you, and for as long as you are here, the echo continues. The universe looks at itself, and it sees you looking back. So where does that leave us? 100 kilometers straight up and you cross a line that exists mostly on paper, a boundary we drew because we needed to draw one somewhere, and on the other side the air thins to nothing and your body stops working in ways that would kill you faster than you could process what was going wrong. 4.2 light-years to the nearest star, a distance so vast that our fastest spacecraft would take 70,000 years to cross it, longer than civilization has existed, longer than we have been behaviorally modern humans. 100 billion dead stars scattered through the Milky Way, stellar corpses outnumbering the living, a graveyard we live inside without noticing because the dead do not shine. 2 trillion galaxies stretched across a cosmic web already tearing itself apart. Expansion accelerating, horizons closing, the universe carving itself into isolated bubbles that will drift apart until nothing can see anything else. And through all of it, the silence. No signals, no probes, no visitors, no evidence that anyone else is out there doing what we are doing. Looking up, asking why. The universe is not hostile. It is not cruel. It does not hate you. It does not notice you. It is a system running its equations, following laws that do not include a term for whether you matter. And yet here you are, a temporary arrangement of atoms that used to be inside stars, powered by light from a star that will outlive your species by billions of years, looking out at a cosmos that will erase every trace of you long before it finishes expanding. You should not be able to understand any of this. Your brain was not designed for cosmology. It was designed for survival, for pattern recognition at human scales, for threats and opportunities within walking distance. And yet you can take that brain and point it at the cosmic microwave background and decode the afterglow of creation. You can measure the acceleration of space itself. You can map the structure of a universe 13.8 billion years old using instruments you built in the last century from materials you dug out of the ground. That is the thing they do not tell you when the scale becomes overwhelming, when the distances and the timescales and the indifference start to crush the idea that any of this matters. You are the universe examining itself, not metaphorically, literally. The same physical processes that made galaxies made you, and the fact that you can look at those galaxies and understand how they formed means the cosmos has done something extraordinary. It has produced a structure capable of comprehension, a way for hydrogen, given 14 billion years, to analyze its own history. You are not separate from what you are studying. You are part of it. A localized increase in complexity, a temporary eddy in the current of entropy, but real. as real as the stars.